Welcome to day 2 of the 2021 NASA STEM Enhancement in Earth and Space Science High School Intern Science Symposium. SEAS is a collaboration between NASA, the University of Texas at Austin's Center for Space Research, and NASA Texas Space Grant Consortium. In 2021, we received almost 800 applications for the final 260 students in the 10th and 11th grades selected as participants, who were then assigned to 14 different Earth and space science projects. Research was conducted in Earth and space science, disaster mapping, climate studies, mission design, and technology. To say these students are amazing is an understatement. Each student conducted 60 to 90 hours of research prior to starting their project, and they heard from 22 NASA subject matter experts during the course of this internship. You are in for a real treat as you hear from these amazing young people, our scientists and engineers of the future. On behalf of Selena Miller and myself, Margaret Baggio, welcome to NASA SEAS 2021. Today, we will have 17 team project video presentations. We will divide the afternoon into 2 sessions with one 25-minute break at 2:05. Team video presentations will either be 5, 10, or 20 minutes in length, followed by questions and answers. Please post your questions on the slido.com website. Use the code SEAS 2021 to enter. You do not need to register. Here is our schedule for the day. We will have presentations by teams, followed by a 5-minute Q&A. We will invite each team presenting to turn on their cameras and their mics to answer the questions posed by those that are listening. During the 25-minute break, we invite you to stick around and watch the video highlights of the student interns as they produced products as part of the Earth and Space Science and Python projects. Our first group today is the Astronomy group. We want to give a special thanks to our project mentors, Dr. Judith Reese, Carrie Johnson, and Olivia Cooper for their guidance and expertise. Our Earth is just a small part of the whole universe. In the Astronomy project, in addition to learning about the scale of the universe, the students have a chance to contribute to astronomy research through citizen science projects. Students worked on the Galaxy Zoo, classifying galaxies, finding clumps, and tracing spiral arm projects. They helped astronomers process the vast amount of data while discovering galaxy types. They made conclusions about star formation, galaxy evolution, and black holes through their research. There will be a total of 4 astronomy teams. We will have questions and answers after team 1 and 2, and again after team 3 and 4. We ask that you post your questions in Slido directed to the team. So you would place team 1 and ask your question. So please join me in welcoming the first astronomy team and their project, Galaxy Morphology.
Our project was the Galaxy Morphology project on the astronomy team. My name is Elizabeth Craig.
I'm Liana Krasnoff.
I'm Catherine Teague.
And I'm Eden Knapp.
So to give you some background about our project, there's a large variety of characteristics possible for different galaxies to have, such as bulges, bars, and disturbances. For our project specifically, our main goals were to classify galaxies according to their shape and characteristics, and then take these classified galaxies and find patterns in the data, and then collaborate with each other to learn more about the evolution and formation of galaxies through our findings. So throughout this presentation, there's going to be some labeled picture representations of what some of the defining attributes we classified galaxies by look like in real life.
This slide shows one of the first slides of some images that we worked with during our Galaxy 2 classification. So on the far left, we have an elliptical galaxy, which is one of the possibilities we could choose to classify a galaxy as. And then in the middle, we have a spiral galaxy, and that was the other possibility for classifying galaxies. And then on the far right, we have a star or an artifact, which was another thing that we could choose to classify some of the images we were working with as.
Our approach to this project was that each group member classified upwards of 40 galaxies for a total of 180 total galaxies. We discovered if the galaxy was spiral or elliptical and looked at its shape, disturbances, rare features, and surroundings. We then took the data and calculated percentages that correlated with how often we saw a certain feature. As we did this, we noted challenges and worked through them as a group. Finally, we discussed our results and the significance of this project.
In our research, the trend that stood out to us the most was how few spiral galaxies there were compared to the number of elliptical galaxies that there were. In fact, out of 180 galaxy classifications, only 22 were spiral galaxies, a mere 12.2%. On the other hand, we found 142 elliptical galaxies, which is around 78.9% of the galaxies we classified. Additionally, we saw 12 disks, making up 6.7% of our data. On rare occasion, we did see a star or artifact, which made up 2.2% of our classifications. Our group discovered a possible cause for this imbalance. Giant elliptical galaxies form from the collision of spiral galaxies, meaning that they are typically older. Since there is evidence the formation of new galaxies is infrequent, this could be a reason why we are seeing so many more elliptical galaxies compared to spiral.
So specifically in terms of elliptical galaxy characteristics, we found that they were mostly an ovular shape, which made up about 45.4% of those that we classified. The next most common was the completely round shape, making up about 37.6% of the ones that we classified. And then finally, there were very few cigar-shaped elliptical galaxies, making up only 17% of those that we classified. And as you can see, there's some pictures on the right. So sometimes it was difficult to tell disks, cigar-shaped galaxies, and edge-on spiral galaxies apart. So we decided to classify disk galaxies in their own category so as not to mistake them for a different type of galaxy. And as you can see on the left, they do look very similar to the cigar-shaped galaxy that we showed in the last slide.
So on the rare occasion that we did classify a spiral galaxy, we found that most didn't have bars in the center. And additionally, about 59.1% of the galaxies had tightly wound arms, whereas only 36.4% had medium wound arms and 4.5% had loosely wound arms. And all of the spiral galaxies that we classified had 1 to 3 arms. Around 55% of these spiral galaxies had a moderately sized bulge in the center, and 45% had a small bulge. And on the left, you can see images of what we mean by tightly wound, medium wound, and loosely wound, and different sizes of bulge in galaxies.
Overall, we found very few disturbances in the galaxies. Disturbed galaxies only made up 17% of our total galaxies classified. When there was a disturbance, it was typically minor, which made up about 60% of all disturbed galaxies. Next was merging galaxies, which made up about 26.7% of disturbances. Finally, there were fewest major disturbances, only making up 13.3% of our total galaxies classified.
Similarly, there were almost no rare features, only affecting 11 galaxies. We most commonly saw overlapping galaxies, which made up 63.6% of rare features in galaxies. Next, we saw 2 rings on galaxies, making up 18.2% of rare features. And finally, we saw 2 irregular galaxies, making up 18.2% of our total as well.
This project allowed us to grasp a greater understanding of galactic evolution, giving us clues as to what galaxies, including our home galaxy, the Milky Way, could eventually look like. This information also helps to provide context and visualization to some questions that have not been answered yet, simply because we have not observed long enough. We also came to understand how rare spiral galaxies were compared to elliptical galaxies in the data found. And even rarer were special features and disturbances, giving to hints as to what the conditions had to have been for these rare features to occur. Spiral galaxies are in many cases younger than elliptical galaxies, which are formed by two spiral galaxies colliding. But just note that distance was not part of the data we were given to work off of, and therefore we could not tell if these elliptical galaxies were a dwarf or a giant. And these are not always younger than spiral galaxies, so they don't apply in all cases. In general, from what researchers have observed, spiral galaxies are identified more often than elliptical galaxies, while elliptical galaxies are estimated to be the most abundant type in the universe. One reason for this could be that spiral galaxies are typically easier to spot since they're brighter. And elliptical galaxies have less gas and dust, giving way to less bright stars, causing them to be dimmer, which is why we don't see as many usually.
Some of the features and challenges of SEAS, specifically the challenges, were that most of us found that we had little prior knowledge or experience in astronomy when beginning this internship. In addition, the astronomy activities were very challenging, but it was very rewarding when we completed them. And sometimes we found that we were unsure of our own skills when we were surrounded by students who we felt were smarter and or more accomplished than us, making us feel a little bit of imposter syndrome. In addition, due to it being virtual, there was more independence in the program, which was a plus, but it also meant that we had to figure out some of the more difficult parts of this program by ourselves with less guidance. In addition, the time restrictions limited the amount of data that we could collect as a group, causing us a smaller sample size, which could cause a less accurate data collection. Additionally, the images of galaxies we classified on Galaxy Zoo were sometimes somewhat blurry, so it was hard to distinguish some of the individual features, which could cause less accurate data collection again. Some of the features of SEAS were that collaboration was a very key aspect. We all had to learn to not be scared to ask questions in general, but also specifically in the virtual environment, and we had to adapt to working with others virtually through Zoom. In addition, we also received extra information and fascinating equipment for being a part of the SEAS program, including a spectroscope, diffraction grading, and a book called The Last Stargazers that described astronomy as a career. In addition, there were live and informative speaker series talks ranging from discussions about careers, internships in colleges, and talking with scientists from many different concentrations across the whole board.
SEAS was tremendously helpful to us for exploring a career in astronomy. It provided us with very experienced mentors that served as role models throughout our years. Experience SEAS prepare us for being later in life. We were given the ability to collaborate and got connections with like-minded peers and mentors. We learned all about the careers that organizations such as NASA has to offer. We got to listen to scientists speak from all areas of astronomy, including astronauts. Some of these concentrations include astrobiology, astromaterials, and scientists and engineers talking about space missions. Finally, we received information about NASA internship opportunities, careers, and even about the University of Texas's programs for aerospace engineering and astronomy.
Lastly, we wanted to close out with some thanks. Thank you for your time during our presentation. Thank you to our mentors during this project. Mr. Johnson especially counseled us through this project, but also gave us the independence we needed to become better thinkers and leaders. We have all learned so much with their help, and we are beyond grateful for this opportunity. We wanted to thank Ms. Selena and Ms. Margaret, who did a fantastic job coordinating the program. And finally, thank you to the National Aeronautics and Space Administration, the Texas Space Grant Consortium, the University of Texas Center for Space Research, the Zooniverse, which was essential to our studies, and the SEAS program. Participating in this program has been a surreal and fantastic experience that will stay with us throughout our lives. Thank you.
Excellent job. Thank you so much. So our reminder, we will have the question and answer session for Team 1 after Team 2's presentation. So our next astronomy project is Team 2 with their research on supermassive active black holes and active galactic nuclei.
Hello, everyone, and welcome to our astronomy presentation on supermassive active black holes. I'm Amelia, and I'm a rising senior at Howard High School in Maryland.
Hello, my name is Crystal Biney. I'm from Houston, Texas, and I'm a rising senior at Cypress Ranch High School.
Hi, my name is Michaela Hansen, and I'm from White Bear Lake, Minnesota. I'm a rising junior, and I attend White Bear Lake Area High School.
I'm Nahum Yeshatilla. I'm from Garland, Texas, and I will be a rising junior at Garland High School.
The Radio Galaxy Zoo LOFAR project focuses on the Low Frequency Arrays telescope image data to classify and detect active galactic nuclei. This project uses a volunteer-led website to efficiently classify thousands of datasets. Our team alone has classified over 350 datasets, which exceeds our 150 goal. The Low Frequency Array, or LOFAR, is an interferometer that ranges in frequency from 10 MHz to 240 MHz. The image on the left shows the several antennas of LOFAR that work together to cover a large area of deep space. The survey data collected from LOFAR is gathered by Fourier transform, which is a computer analysis. This process creates the yellow radio emission lines shown on the classification. Since we cannot rely solely on the judgment of a computer, the human classifications must be completed. The antennas of the LOFAR telescope are located all around Europe, as shown on the image to the left. LOFAR is a unique telescope because it is composed of thousands of antennas that work together to create one big telescope. The LOFAR telescope creates high-resolution images that inform us about the earliest events of our universe. This project aims to analyze data in the northern portion of our sky. The image on the right shows the location of the datasets in their status of completion.
So in all this data, we're looking for AGNs, or active galactic nuclei, which are the highly luminous regions at the center of active galaxies that emit tons of electromagnetic radiation. In the top image on the slide, you can see the AGN is a really bright area in the center. It can also be identified from the LOFAR data, such as in the bottom image, by the yellow bands, which represent radio emissions. The radio emissions could be coming from a variety of different sources, but they suggest the presence of a supermassive black hole when there are two main lobes on either side of a potential source, such as in the left image that could be optically identified, which come from the jets. So the jets are a stream of light spanning the entire EM spectrum and can be seen in the top image running perpendicular to the dust cloud. Finding AGNs helps hint at the formation and evolution of active galaxies, which plays a huge part in the evolution of the galaxy as a whole. So here we have 4 different types of active galactic nuclei, classified by their electromagnetic spectral emissions. First, the Type 1 Seyfert galaxy has both narrow and broadened spectral emission lines, whereas the Type 2 Seyfert galaxy only has narrow emissions. And blazars don't contain emission lines in their spectra at all, whereas quasars have weak narrow emission lines. So this is how we classified our data on the Zooniverse site. The first step was to figure out which of the dashed ellipses we believe were components of the single solid ellipse, and we just placed a single marker in each one, as seen in the image below.
For task 2, from the optical image background, we are looking to find the source of the radio emission structure that is circled by the solid blue ellipse, labeling that source with a pink marker. For task 3, the Zooniverse users point out any of the possible problems that they may observe in a given image, and we will show examples of these problems in the next slide. So a star can potentially become a problem if the bright light from the star obscures the identification of the components or the source of the radio emissions. And an artifact occurs when the radio or the yellow contour lines seem to be very spread out, or they seem to have no clear shape. And artifacts are caused by whenever the computer program, which is responsible for transforming the raw data collected by the LOFAR telescope into the yellow contour lines that we see in the image, when that computer program fails to properly correct for the corruption of the Earth's atmosphere or the corruption of the radio signals by the Earth's atmosphere. And a blend is caused by when the source finder algorithm incorrectly associates 2 or more sources within a single ellipse. For the last task, we determined which black hole images have an active or inactive galactic nuclei according to whether the yellow contour lines, which represent the radio emission, whether those lines have a double-lobed AGN jet shape. And it is through this process of analyzing the activity of the galactic nuclei that scientists have been able to discover new evidence from double-double radio galaxies, which suggests that the activity of these active galactic nuclei may change over time.
Statistics, total classification of AGN. Here's a chart of our classifications of active galactic nuclei with over 400 classifications in total. We have put together a visual pie chart which displays that roughly half of the data we observed contained an inactive galactic nuclei, while the other half did have an active galactic nuclei. Why is it important to study active galactic nuclei in supermassive black holes? Well, AGN can reveal a lot in the study of supermassive black holes. It allows us to visualize how galaxy clusters and black holes formed. For example, quasars appear to live in galaxies, so they can help us understand galaxy formation and evolution. It also helps us understand the magnetic field in our universe. Radio emission from AGN is synchrotron radiation, which means electromagnetic radiation is emitted when charged particles are accelerated radially. Therefore, it is generated by energetic particles in magnetic fields. So wherever we see radio emissions, magnetic fields are also being traced and can estimate the field length. Studying AGN can also create a picture of the earliest occurring star formation. Research of early star formation is not related to observing AGN, but among the objects studied are many star-forming galaxies, where the radio emission comes from stellar processes and is not related to jets. One can trace star formation in the distant universe by identifying those objects and distinguishing them from AGN. Lastly, it allows us to explore frequencies never observed from the universe, leading to new discoveries. Here are the highlights of the NASA SEAS program. NASA SEAS has allowed my group to undergo great intellectual discovery. We have studied in great depth active galactic nuclei, LOFAR, and supermassive black holes. We have also acted as real astronomers and have classified over 300 pieces of data. And working together as a team and learning together as well, we have developed a close bond among ourselves, along with our amazing mentor, Olivia Cooper. Though there were many amazing features, there were also a few challenges we had to overcome as well. The challenge of virtual collaboration was present, having to work across different time zones and working on projects at different times altogether. Data classification was unique to other types of projects we have done in the past before, as there was very little quantitative data and our analysis was purely based off of observation. NASA SEAS has allowed me to explore different fields, which I now will consider studying in the future. I hope to continue my astronomy journey through my university years.
The NASA SEAS internship has definitely paved the way for my future in STEM. It has shown me where my passions lie and will definitely help me in my future.
SEAS was a great opportunity to explore different careers in STEM.
SEAS has greatly enhanced my understanding of and love for many scientific disciplines relating to space. And I'm very grateful for this opportunity and the memorable experiences that I have had over the course of this incredible program.
If you want to learn more about the Radio Galaxy Zoo LOFAR project, then you can scan the QR code on the top left-hand corner. Citizen volunteer projects like this allow millions to share their passions for STEM and space science and allow the enhancements in space discoveries. And here is our works cited.
We'd like to give a big thank you to all of the astronomy mentors, all of the SEAS staff involved in making this program possible, the Texas Space Grant Consortium, Zooniverse, Martin Hardcastle, who is the Zooniverse project scientist who directly worked with our group to help us in our research, and NASA.
Great presentation. So astronomy teams 1 and 2, we invite all participants to please turn on your cameras and your microphones. We have several questions for you. The first question is for team number 1. Can you please explain how you made judgment about the age of elliptical galaxies?
I can take this one. So in terms of ages of elliptical galaxies, when we said that the reason we saw so many of these was because they were formed by colliding spiral galaxies and therefore older, we were only posing a possible explanation for this. And as we mentioned in the significance slide, distance was not a part of our research, so we couldn't tell how far away the galaxies we were classifying were, and therefore we could not tell the size of elliptical galaxies or exactly how they formed. And because of this, we were unsure if they were dwarf or giant elliptical galaxies, so age was not completely clear, so we didn't base a lot of our research off of that.
So the next question for team number 1, could the view angle affect how difficult it is to identify a spiral galaxy?
I can get this one. The view angle absolutely could affect how difficult it is to identify spiral galaxies. For instance, with edge-on galaxies, it was often nearly impossible to tell which type of galaxies they were and the characteristics that they had. So in that situation, we simply made disk galaxies or edge-on galaxies a entirely separate classification just to be sure. And additionally, this wasn't necessarily an angle, but many images were blurry, and that also was a challenge in identifying what type of galaxies our images were.
How did you make the distinction between a face-on spiral galaxy and a circular elliptical galaxy at high redshifts?
I can take this question. So in the Galaxy Zoo website, we all looked really closely for the spiral arms on the galaxies we were studying. And on the website, we were actually able to invert the colors on the image to be able to see more clearly if there were arms in any of the galaxies, which allowed us to have more certainty in the galaxies that we are classifying. And in the end, if we couldn't tell, we would all come together to work on classifying the galaxy together rather than doing it individually. And we came up with like our best group educated guess. In addition, all the spiral galaxies that we ended up classifying had fairly defined shapes, whereas we found that the high redshift circular elliptical galaxies could be somewhat irregular and blurry. So that also helped us in making the distinction between the face-on spiral galaxies and elliptical galaxies at high redshifts. So yeah.
Team number 2, what causes the double-lobed shape seen in the AGN resources?
Double-lobed shape comes from the jets. You can see in the image on the slide, actually, the jet is running perpendicular to the accretion disk, which is, that's just the main plane right there. But the light from that, it spans the entire EM spectrum. So you get radio emissions off of that, and that causes the double lobes on either side of the source.
And the next question is also for team number 2. How did you distinguish active and inactive galaxies from each other?
Well, that was actually task 4 of our data classification, and we did that by looking at whether the radio wave lines were in the jet lobe, the lobe shapes.
And this question is for both teams, so whomever would like to answer. Is there anything you would change or modify with the Zooniverse interface? How did you guys go through the galaxies on Zooniverse together?
For our group, at least, we found some difficulties in classifying the galaxies because of the blurriness. And of course, it's a difficult problem to solve, but sometimes, as Katie mentioned, we just had to take an educated guess. And we went through the galaxies together by creating a spreadsheet as we classified each of our own. And then we came together as a group on a Zoom call, and we discussed our results, and we came together and we found trends in our results.
Yes, and for the difficult ones, we also pulled those up and said what we each thought it was. And yeah, but overall, we thought that Zooniverse was a very good interface. It was very easy to understand and easy to go through.
Team number 2, the comment is great project. Any reason the LOFAR satellites are in the Northern Hemisphere?
That's actually a really good question. And we did not actually study where they are in the Northern Hemisphere, but I think it's because the project is originated in more the Northern Hemisphere. And that was also a difficulty when having to collaborate with the team leaders because of the time zones, but we don't actually know the answer to that question.
So team number 2, what other tools did your team use to classify formations? Did you primarily use visual interpretation, or were there other tools that you leaned on?
So visual interpretation, mainly with the yellow contour lines, that's where we made most of our decisions based on, that dictated a lot of the problems that we were seeing there. like with the artifact and the blend. But yes, it was mainly just visually.
And then this is for both teams. So we'll ask for a volunteer from team 1 and team 2. If you could just wave a magic wand and create additional hardware assets to assist in observing this data, what would it be and where would it be located?
Well, for the black hole project at least, it would have been really nice if we could get like really zoomed in on images of the galaxies and actually just see the black hole. Obviously, that's like way in the future, but that would have helped a lot with ours.
I would also like to add that one of the challenges for classifying the data was being able to, there wasn't as much quantitative data, it was more based off of our interpretation. So being able to have more of that, like such as the distance of the, or like the width of the contour lines, which represented the radio emissions. So having that would have made it easier to classify the black holes as being active or inactive.
And for the galaxy classification team, in our case, we would have liked to know distance if we could just wave a magic wand. And that would also be able to help us know if a galaxy was a dwarf galaxy or a giant galaxy. And that would really help in us knowing more about the evolution of galaxies and the age of the galaxies as well.
So this question is for team number 1. How exactly did you classify your galaxies?
I can take this question. So we used the Galaxy Zoo application to classify the galaxies, and it provided us with an image and asked us questions to guide our classifications. It first asked us whether it had features of a disk or if it didn't. And if it didn't, it asked us questions about the roundness, any disturbances, or any special features if they were present. If it did have features of a disk, it asked us if it was from an edge-on view or not, because if it was from an edge-on view, it's hard to tell any features from there. But if it was not from an edge-on view, it also asked us about like the tightness of the arms, how many arms, any bars, bulges, disturbances, or made a final classification group.
The next question is, how easy or difficult was it to use Zooniverse?
So for the supermassive active black holes group, Zooniverse is actually very user-friendly. So you're not doing these projects by yourself. You have a group of other volunteers. There are thousands of people that also want to help classify supermassive black holes. And there's also tutorials, so you can, you're not just jumping into the project without any prior knowledge. And the tutorials are very go in depth about the project and what you're looking for and things that may appear confusing. So it's very helpful.
Yeah, for group 1, we all found that Zooniverse was a really great tool and resource to use when we were classifying the galaxies. Just like group 2 had said, there was a lot of training on the website and there were references and guides that we could use while we were trying to classify the galaxies, which was really great for all of us because we didn't have very much experience in galaxy characteristics and classifications prior to this project. And it was pretty helpful because it was kind of like a survey that we would go through each time we were classifying the galaxies, which made it fairly easy for us with not much background experience to use.
And then for team number 2, did you find many optical counterparts to jets?
So with the sources for most of the AGNs, when we were looking for sources for the radio emissions, they were there some of the time, but also it was kind of hard to tell because if there's a blend, then it could be coming from multiple sources, or, you know, if a star was in the way again, then it's hard to differentiate between what's the star and what's actually the, like, optically identifying the source as well. So it was definitely there some of the time, but other times it was difficult to determine which one was actually which.
Well,
I would
both-
also like to add that this is why we need human classifications, because the computer sometimes can mix the radio emission lines with the supermassive black hole lines can mix with the star lines, and this is why they need a human eye to classify this data.
Well, terrific job. Both of your teams have done an amazing job. We appreciate your presentation, and thank you for all the awesome answers to the questions. So we will move on to our next Astronomy Team 3 presentation. Their research is on a sample of SDSS galaxies used to investigate galaxy evolution.
Hello, everyone. We are the Redshift group, and our project was about taking a sample of galaxies from the Sloan Digital Sky Survey and looking at their redshifts to get a picture of the evolution of galaxies in our universe. My name is Nathan Streeter, and my teammates are Karis Hall, William Osling, and Nidhi Shah, and this is our presentation.
The idea of redshift is that when an object is moving away, it's slightly redshifted on the visible spectrum. The diagram on the bottom left shows the Doppler shift, where when the star is moving away, the light waves are elongated, which moves the light towards the red side of the spectrum, and vice versa to the blue side for objects coming closer. Later scientists made the connection between redshift and the general expansion of the universe. This cosmological expansion differs from the Doppler shift because the objects are not moving away, but rather the space between them is expanding. The raisin bread diagram on the right demonstrates how this expansion works. The bread is a space which is expanding and causing the raisins, the matter within that space, like galaxies, to move away from each other. Specifically, raisins that started out closer together moved smaller distances away from each other compared to those that started out further apart. This holds true for any raisin and means that the further a raisin, the faster it's moving away. Using this rule of cosmological redshift, almost all objects in the universe can be seen to be moving away from us, and the further these objects are, the faster they're moving away. Redshift allows scientists to measure the most distant galaxies, and since light takes time to reach us, this allows scientists to look into the past at the early universe. Understanding these trends is very important in understanding how the universe began and evolved and how it will continue to do so.
So our main goal for this project was to explore whether or not there were any correlations between galaxy redshift and galaxy type by compiling, organizing, and studying a database of over 200 galaxies. We aim to collect specific measurements and note any possible biases that may have altered our results and data. This would hopefully help to answer questions on topics such as the evolution of galaxies and early universe conditions. In order to achieve these goals and complete our study, we used data and measurements from SDSS, the Sloan Digital Sky Survey, Data Release 6. Each group member classified over 50 galaxies from the plates of the SDSS archives and also noted the galaxy's right ascension, declination, redshift, and the redshift error. Using tools such as visual images and galaxy spectra, we were able to classify these galaxies by their morphology and distinguish whether or not they were considered active or non-active galaxies. From there, we could organize all this data and search for trends or patterns. These are some examples of different types of galaxies and their respective spectrums that we encountered and classified through our research. We also have examples of galaxies that were more challenging to classify due to factors such as high redshift and distance or low image resolution. And finally, we have an example of a unique ring galaxy we were able to find and classify through our research. Displayed here, we have galaxies demonstrating the difference between non-active and active galaxies. An active galaxy is defined to be a galaxy with an active nucleus, containing a black hole gaining mass by feeding on the surrounding material. As this material spirals into the black hole at the nucleus, it reaches high temperatures, exciting the surrounding gas, resulting in emission. So one of the ways we can tell whether or not a galaxy is active is by searching the galaxy's spectra for emission lines. As you can see, the active galaxy's spiral spectra indicate strong H-alpha and oxygen emission lines, while the non-active galaxy's spectra does not, and also contains a few clear absorption lines. These are all factors we would take into account in order to classify each galaxy as active or non-active.
While analyzing the data, we found sources of bias, which we worked to eliminate. We found more elliptical and spiral galaxies than interacting and irregular galaxies, giving us less data to work with in those categories. We also found a lot more galaxies at low redshift, simply because those galaxies are larger and brighter, making them easier to spot. We noticed that at higher redshift, there was generally a higher redshift error. This is simply because at a higher redshift, galaxies tend to be much dimmer, so their spectrum is a lot noisier, making it harder to accurately determine their redshift. To combat this bias, we used percentages and composition instead of initial count. We also noticed that the redshift range from 0.2 to 0.3 had a deficit in our original sample, so we added 30 additional galaxies around that range. To create the pop graph, we split redshift into 10 bins, then totaled the amount of galaxies per bin and created percentages for each galaxy type. We decided to add the percent interactive and irregular galaxies simply because it was hard to tell them apart at such a high redshift. From the graphs below, you can see a third order polynomial fitted line is fitted. And you can see that more irregular and interacting galaxies appear at higher redshift. This is because we see them farther in the past when galaxies were closer, and so they had much more of a chance of interacting. We also see more spiral galaxies at a low redshift, and this is because we see them closer to real time when they have less of a chance of getting disrupted because galaxies are farther apart. This graph details the percent makeup of active galaxies versus redshift. The large amount of active galaxies at a low redshift is contaminated by spiral galaxies, most of which we see have starbursts, and so they appeared to be an active galaxy. The slow rise between 0.1 and 0.4 redshift corresponds to true active galaxies, and the sharp cutoff at around 0.5 is where SDSS cuts off H-alpha lines due to telescopic restrictions.
One of the challenges we had during this project was that classifying the distant galaxies could be difficult, since sometimes they were only pixels across in the image. In addition, some images would unfortunately have artifacts like misaligned plates, which could leave parts of the image as the wrong color or offset and misshapen. Another thing to keep in mind was that there was no magic number or way to tell apart different types of galaxies 100% of the time. Often we were making our best judgments when we were classifying these galaxies. Working over Zoom also brought its own challenges, like a time difference between some of us, and we were also only able to classify around 230 galaxies, which might not have been a large enough sample to remove some of the biases in the data. Our final main challenge was the limitations of the telescope used for the survey, like galaxy spectra being cut off and detecting far more low redshift galaxies than ones that were farther away. However, we did have several big highlights and favorite parts of the internship. We got to see a wide variety of galaxies, from massive nearby grand design spiral galaxies to the interesting ring galaxy and faraway blobs with no real shape. We were also able to use helpful visual tools and spectral images of galaxies to make our classifications easier and more accurate. Also, being able to work with students and mentors that shared an interest in astronomy and research made SEAS just that much more engaging.
So for me, the SEAS internship not only taught me new skills and techniques in areas including astronomy, scientific research, and computer science, but it also reinforced my vision of a future career in astrophysics and space exploration. It helped me to realize the possibilities and encouraged me to explore different aspects of that career path, including striving for a career with NASA and applying to be an astronaut in the future.
My time at SEAS strengthened my passion for observational astronomy. I've always loved astrophotography, and so analyzing real telescopic data that researchers use was really amazing, and spectra analysis was something new and fun to learn. I also learned many new skills, like querying and analyzing survey data and creating graphs in Python meant to remove as much bias as possible.
Being a SEAS intern taught me what exactly an astronomer does and how various skills, many of which I hadn't considered before, can be used practically. And most importantly, I learned about the various skill sets involved in NASA's work and more about the professional career that I might want to pursue.
I really enjoyed the speaker series where I got to learn about the wide variety of research fields in not just astronomy, but Earth and space science as a whole. I also got an in-depth look at astronomical research and new scientific concepts with real galaxy data.
This work was made possible by our amazing project mentors and astronomy group leaders, Dr. Judith Reese, Olivia Cooper, and Carrie Johnson. The SEAS Association and NASA made this entire program possible, and the Sloan Digital Sky Survey and the European Space Agency made all their data public, allowing us to survey it.
Excellent job. So we will remind you to please put your questions in the Slido website and identify which team the question is for. So thank you for a great job, Team 3. We will move on to our next astronomy project and their presentation on dark energy explorers.
We are the Dark Energy Explorers with HETDEX. My name is Audrey Hopkin.
I'm Charlotte Myers.
Dia Kumar.
And I'm Madison Brown.
Before we dive into the research, let's cover some background information. What is dark energy? The short answer is no one knows, but we're almost certain it exists. Much like dark matter, we can't detect it directly, but rather can only observe its influence. As more research reveals its significant impact on the expansion and evolution of the universe, more and more astronomers are seeking to unravel the mysteries of dark energy. The first evidence for the existence of dark energy arose in 1998, when two independent teams of astronomers made the same surprising discovery. Both teams were studying Type 1a supernovae, which brighten and fade in predictable cycles that allow astronomers to reliably determine their distance. When comparing this value to the distance calculated using their redshifts, they could infer the universe's rate of expansion. We've known that the universe is expanding since 1929, when Edwin Hubble published a paper detailing the correlation between a galaxy's velocity and its distance from us, shown in this graph on the right. However, how this rate of expansion changes tells us about the ultimate fate of the universe, and this is what teams of astronomers are trying to determine. In the supernovae study, it was found that these stars were farther away than expected, meaning they did not fit Hubble's model. In other words, the old model not containing dark energy does not fit the data at higher and higher redshifts. They came to the conclusion that the expansion of the universe is accelerating. The invisible force that causes the expansion to speed up was named dark energy. Though we don't know exactly what it is, we can clearly see its effects on the nature of the universe.
So what does this mean for science? Dark energy completely changed the way cosmologists understood the future of our universe. After Hubble's discovery, the prevailing theories were that the universe's expansion would either reverse or slow down and come infinitely close to stopping. If there's enough matter in the universe, gravity would be the dominating force. Eventually, the universe would shrink back into a singularity and possibly start expanding again in an infinite cycle. This was called the Big Crunch or Big Bounce scenario. If there wasn't enough matter to cross the threshold, however, they thought eventually the expansion would slow down until it became imperceptibly low. And eventually all the stars would burn out, all the galaxies would dissolve, and all the black holes would evaporate. This was known as heat death or the Big Chill scenario. These scenarios become very unlikely once we take dark energy into account. Since the expansion of the universe is speeding up, it's more likely that galaxy clusters will move farther and farther apart, faster and faster, until they get to a point where the light emitted by them will never reach other galaxies. This sounds impossible, but the universe can actually expand faster than the speed of light. While matter itself can't move through space faster than that, space can stretch at such a rate. So eventually there will be a time when we won't be able to see other galaxies. Eventually these will dissolve and space will expand between individual atoms so fast that they'll never interact with anything else ever again. Our project is to aid in citizen science for the Hobby-Eberle Dark Energy Experiment, or HETDEX. HETDEX's goal is to create the largest map of the universe yet by measuring around 1 million galaxies 9 to 11 billion light-years away, or with a redshift value of 2 to 3. This map will help astronomers understand the influence of dark energy on the universe's expansion throughout time. This map will be made of 150 spectrographs called the Visible Integral Field Replicable Unit Spectrographs. These spectrographs gather light from galaxies and split them into their spectra, which can reveal the galaxy's chemical composition, its redshift, and the speed it's moving away from us. Astronomers then convert the object's redshift or its motion away from us into distance, and they can then produce maps of our universe.
The next step astronomers take to determine the influence of dark energy is through using a concept best explained by studying baryonic acoustic oscillations, or sound waves, from the first 400,000 years of the universe. In the early years of the universe, it was very dense, compact, and a liquid-like mixture of matter and energy.
Sound waves created by disturbances rippled across this dense universe, and at about 400,000 years, the universe became cool and thin enough for the ripples to cement into a specific size. Telescopes have measured the crest of these ripples in the universe, and that forms a basic measurement. As the universe expands, this basic measurement is kept, though it does grow as the universe grows. HETDEX uses this concept of a basic measurement by measuring the distances between distant galaxies at different times in the early universe. The maps created with the galaxy's redshifts are incredibly important here, as the astronomers want to measure distances between galaxies that are within the same time period or have a similar redshift. By observing how the distance between galaxies has changed with respect to time, we are subsequently observing the influence of dark energy with respect to time, or its influence at different epochs in the universe's history.
Our task was to sort between nearby and distant galaxies. We filtered out images that were just noise, nearby galaxies, or stars, so that the data wouldn't be contaminated by non-distant galaxies. Our work, as well as the work of other citizen scientists, helps astronomers to develop confidence in their classifications of distant galaxies. They will then be able to create a detailed map that will be used to calculate the change in the expansion rate of the universe over time, revealing the role of dark energy at different eras of the universe.
This is how we collected the data for our project. We were given images like the one you see on the left. It has 3 components. First, we could determine if what we were looking at was an actual object or if it was just noise or static. The 5 panels on the left and the spike at the bottom help us determine that. If no black dot appeared in any of the panels, or if the data points didn't correspond well with the line, then we classified it as noise. If there was a black dot and the data corresponded well, it was an actual object. Then we'd look at the top right image to determine whether the object we were looking at was a nearby galaxy or star, or if it was actually a distant galaxy. If the black region was larger than a certain threshold indicated by those small colored circles, then we classified it as nearby. If it was smaller than the circles, we classified it as distant.
As previously shown, galaxies are classified primarily based upon the relative size of the dark circle in comparison to the colored circles. These colored circles are given by the research team on Zooniverse.org. On the very left, the dark circle is larger than the colored circles. Therefore, it is classified as a nearby galaxy. The middle image shows the opposite of this. The dark circles are smaller than the colored circles. Therefore, this is classified as a distant galaxy. On the right image, there is not an exact dark circle to be used for comparison, nor does the spectral line graph demonstrate a real source as mentioned within the last slide. As seen on the pie chart on the right, you can observe the actual data distribution of galaxy classifications in the given catalog. 42.8% of the given catalog were distant galaxies, 47.2% were nearby galaxies, 7.9% were found to be noise, and 4.4% of the data samples were difficult to identify. The 4.4% of data samples that were difficult to identify provides an estimate of the error for all groups. Additionally, observational bias had the potential to influence error and data observation. We're closer to the nearby galaxies. Since these stars and galaxies are bright, this may appear more frequently within our data catalog. Essentially, HETDEX aims to identify galaxies of interest, that being distant galaxies 10 to 11 billion years ago are light and alpha emitters.
This reveals that a lot of the data in the catalog right now is misleading and needs to be filtered out, as a large majority of them are not in the desired redshift range. Over half of the data is comprised of nearby galaxies, stars, and noise, when the scientists only want to look at distant galaxies. This also tells us that more people need to get involved for the project to succeed. It's a fairly new project, which requires a lot of confidence in the data being used. A lot of the data we are asked to sort through can be ambiguous, with it being hard to identify distant galaxies from noise, and sometimes even nearby galaxies or stars with distant ones. Involving more people will eliminate any error that an individual citizen scientist makes and result in a more successful project.
Additionally, computers are not as accurate as human visual classification. They often pick up too much noise from surrounding celestial bodies. Visual classification allows for the development of AI computer algorithms to classify nearby or distant galaxies. Understanding the approximate error and difficulty in human classification will provide a basis for computer algorithms, thus expanding the understanding of the error on future computer algorithm galaxy classification systems for HETDEX. This, in turn, provides a rationale for citizen science for this project.
The CEASE program allowed us to explore methods of contributing to astronomy research as high school students. By utilizing citizen science projects, we were able to contribute to astronomical research in an environment that was suitable for our ability and instrument accessibility, while also challenging and encouraging our background knowledge. The challenge, of course, was the virtual environment, which added a barrier to communication and the type of work we were able to perform, though we still did get a lot out of this experience. This opportunity was invaluable to us, and we're extremely grateful to have been able to participate.
We'd also like to acknowledge and say a big thank you to all of the SEA's mentors, organizers, and presenters.
Terrific. So we have some amazing questions. I want to invite the Astronomy's teams 3 and 4 to please turn on your cameras and your microphones. The first question that we have is for team 3. It says, you mentioned that classifying galaxies isn't an exact science. Why is that? And what did you do to rectify the situation?
I can take that question. So classifying galaxies isn't an exact science simply because we can't really pin down specific categories. A galaxy could look like a spiral galaxy, but it could have other features of an elliptical galaxy. And so it would be hard to place a galaxy in either a spiral or an elliptical category. And so what we try to do is what would make it a more exact science is put very specific boundaries. For instance, saying an elliptical galaxy has to have these features and nothing else, because otherwise galaxies can pretty much be almost classified as anything.
The next question is for team 4. Is there a correlation between the amount of dark energy and the type of galaxy?
I'll take this one. Not necessarily. Dark energy, we describe it as the sort of pressure that's causing the universe's expansion to speed up. It doesn't necessarily change the type of galaxy that we have, but it does influence how fast they're moving away from us. So I suppose you could say if there is more dark energy, the galaxies, there would be more distant galaxies, but I think we also explained that we did get more nearby galaxies just due to the fact that they're easier to detect. So there isn't totally a correlation between the amount of galaxies that we found as either distant or nearby, but rather we're using this data to create a map that might be able to give us more insight into the amount of dark energy.
The next question is for the Redshift team. What was the farthest galaxy that you classified?
I can take this question. The farthest galaxy that we found was at Redshift 0.571, I believe. And that means that the light emitted from the galaxy took, I believe, around 5.7 billion years to reach us. I'm sorry, I don't know the exact distance to the galaxy right now, but it is certainly farther than 5.7 billion light years simply because of the universe's expansion. But more importantly, that very far away galaxy, which showed up as just a faint blob, we classified it as an irregular galaxy, I believe. It was quite a peculiar shape, if I remember correctly.
The next question is for team number 3. What did you learn about dealing with the uncertainty in classification process?
I can take this one. So it's definitely very difficult dealing with that uncertainty because we obviously wanted to kind of be certain about which type of galaxy it was, but we basically just, as a team, shared our thoughts, what each of us thought it was, and tried to use as many resources as we could. And along the way, we did get better in trying to see the different signs and markers in the image and in the spectra, and just made our best educated guesses.
Team number 4, how can you measure dark energy if no one really knows what that is?
I can take this one. That's a really good question. So we're not exactly measuring dark energy. We're measuring its influence. So the way we did this was by observing the acceleration, or the way that HETEX is doing this is by observing the acceleration of our universe, by looking at the distance between galaxies and how that distance changes over time. And the different rates at which the universe is accelerating, or at the different rates at which the distance between the galaxies is changing, reflects dark energy's influence and effect on the universe at different epochs.
So the next question is for team number 4. How can people get involved in a project like this? What kind of information would improve machine learning, in your opinion?
I can take this one. So essentially, people can get involved in this project by going to universe.org. It's a very user-friendly website to use, and simply classify the galaxies on either the mobile app or on a computer. And how to get people interested in this project is simply by finding astronomy fans or people who are interested in the subject matter. Additionally, what kind of information could help improve this machine learning? What Universe does and the people involved within this project is they'll take the classifications from human visual classifications, and they will put that in their machine learning. And that's essentially what they do, is they're building upon what our data gives to them to advance the machine learning right now, because the machine learning right now is currently not to the point where it can accurately classify galaxies and whatnot.
So this question is for both teams. Did either of you have the opportunity to compare SDSS and Galaxy Zoo data?
I can take this one. So for our project, we just used SDSS data. We didn't actually have the opportunity to compare it with any other data from the Galaxy Zoo website.
And then for the dark matter team, what does integral field mean?
I'm not sure exactly what integral field would mean, because we got the name from Virus, which is the spectrographs that are on top of the Hobby Eberly telescope. But an integral field unit, which is what I learned about when we were researching this project, is basically when the field of view of a unit, which is something that they developed, was the integral field unit, is when the field of view is basically divided into a bunch of like little segments so that I can create a comprehensive picture rather than one unit taking in all of the information at once.
And the Redshift team, did you find any active elliptical galaxies?
I can take this one. So we did find 1 or 2 active elliptical galaxies, and they looked pretty elliptical in the optical view, and their spectra had typical elliptical curvature, except for extremely strong H-alpha and oxygen-3 ionization.
Karis, I think you wanted to add something to that.
No, I was just going to agree with him and say we did find a few. However, the most common was active spiral galaxies. That was most common throughout our research.
Well, you have both of your teams have done an amazing job. I say congratulations on your research. I look forward to seeing what your future holds. So we are going to move on to our next project group. And our next project is Weighing Earth's Water team. We want to give a special thanks to Corinne Bassilo for her guidance and her dedication to working with these students. Interns analyzed the data from the GRACE, which is NASA's Gravity Recovery and Climate Experiment, twin satellites that launched in March of 2002, and GRACE-FO, which launched in 2018, that are making detailed measurements of Earth's gravity field changes and revolutionizing investigations about Earth's water resources over land, ice, and oceans, as well as earthquakes and crustal deformations. These discoveries are having far-reaching benefits to society and the world's population. So here is the Weighing Earth's Water team and their project, Gravity Recovery and Climate Experiment.
Hello, we are the GRACE team. I'm Lindsay Beer.
I'm Ethan Chandra.
I'm Vardhini Karthik.
I'm Anjali Koda.
I'm Scarlett Pinky.
And I'm Nina Ryan.
And we also have our amazing mentor, Corinne Vassallo.
This summer, we continued to take early steps towards the ultimate goal of understanding whether machine learning can be used to identify changes in groundwater storage using GRACE satellite data. However, this is a pretty ambitious goal, so we did narrow our focus to answering the question, can a machine learning algorithm be used to learn anything about hydrological signals seen in the GRACE data? In today's presentation, we're going to start by talking a bit about the GRACE mission and its data product, equivalent water thickness values. We will talk about the need for a model data set, in this case, the AOHIS data set, as well as explain how we can use the two in conjunction with a machine learning algorithm. We will share our results from some tests that we ran and finish with some reflections from this summer.
The GRACE mission, which stands for the Gravity Recovery and Climate Experiment, was originally launched in 2002 and remained in orbit for 15 years. Following the conclusion of the original GRACE mission, a second mission called GRACE Follow-On was launched in 2018 and continues to produce datasets each month. The spatial resolution of the GRACE mission is available for spherical harmonic degree order 120. Both missions involved two identical satellites that measure anomalies in Earth's gravitational field by calculating the distance and change of distance, or range and range rate, between the two satellites. The measurements made by these satellites are extremely precise and can detect changes as small as 1 micron or 1/10 of the width of a human hair. The maps produced from GRACE data, as shown in the bottom right-hand corner of the screen, provide detailed information about water in lakes and rivers, groundwater storage, soil moisture, and ice melt in locations all around the world. The maps that are created from GRACE data can be used to monitor droughts, flood potential, groundwater storage, and ice melt. And the observations made by the GRACE satellites can be used to understand more about rising sea levels and Earth's water cycle as a whole. Although it can be somewhat confusing to look solely at the maps created using the numerical data that is recorded by the satellites, the maps that are created using this data can be applied to many real-world situations. Producing monthly maps like the one pictured on the left-hand side of the screen can allow scientists to track surface mass changes across the planet and watch as water moves around the Earth. For instance, the region at the top of the May 2021 map that is almost entirely red is Greenland. The red values correspond to low equivalent water height values and tell researchers that during the month of May, Greenland was losing mass in the form of water. The main factor that impacts the distance between the two satellites is variations in the distribution of Earth's mass caused by moving water. Since the strength of gravity is directly proportional to the amount of mass that an object has, variations in water storage can impact the local gravitational force exerted on the GRACE satellites, which can cause the distance between the two satellites to change slightly. In the diagram to the left, the red arrow represents the satellite's horizontal speed, and the blue arrow represents the gravitational pull on the satellites based on the mass distribution of Earth. In the first panel, it can be noted that the red arrows are the same length, which denotes that the satellites are traveling at the same speed. In the second panel, the leading satellite approaches a landmass and begins to accelerate forward because of the increased gravitational pull. This causes the distance to increase between the two satellites. In the third panel, the trailing satellite begins to feel the landmass's gravitational pull and accelerates while the leading satellite passes over the landmass and begins to slow down as it is held back by the remaining gravitational force. In the final panel, we can see the distance between the two satellites return to normal as they pass over the landmass. The range and range rate values recorded by the GRACE satellites are used to calculate gravitational potential, which can be expressed using spherical harmonic coefficients. The image on the upper right-hand side of the screen depicts three kinds of spherical harmonics. Taking the sum of models like these allows for complex geoid maps, like the GRACE gravity geoid pictured in the bottom right-hand corner, to be created using GRACE data. Additionally, using the potential, the equivalent water thickness can be calculated as well. Ethan will discuss more about the equivalent water thickness in the next slide.
Equivalent water thickness, or EWT for short, is a way to represent GRACE data in a meaningful way. Instead of measurements of Earth's gravity field, these values are converted into the amount of water that is distributed throughout Earth. EWT calculates the variations in water storage deviated from the average, which is caused by the movement of water throughout Earth, measured as a thin layer of water in centimeters. And to demonstrate what an example of EWT may look like, this image below, which is a US map of EWT data over a 9-year period, represents the changes in water storage from heavy drought in severe red and abundant water storage in deep blue, with respect to the scale from -11 to 11 centimeters. And demonstrated in 2011, in the northwestern region, we can see that there is significant water storage. In contrast, in the southern region, we can see that there is a heavy drought.
So in the beginning, we talked about the AOHIS dataset, which we're going to be using in conjunction with the GRACE dataset for a machine learning algorithm. But what is the AOHIS dataset? AOHIS is a model dataset created by the European Space Agency, and it runs from 1995 to 2006. It models water variability with respect to time. It accounts for gravity changes from a variety of events, from atmospheric mass anomalies to ocean water, to terrestrial water storage, which is also known as the hydrosphere, to ice sheets, to solid land masses, hence the name AOHIS. Its temporal resolution is 6 hours, and its spatial resolution is spherical harmonic degree order 180. The reason for a model dataset is because the GRACE data spans from 2002 to 2016, which isn't enough time to record all possible hydrological events that could happen. While the AOHIS dataset doesn't extend much beyond that time period, the similarities between GRACE and AOHIS means that we could use the AOHIS dataset to see if any model dataset could work with the GRACE data. Anjali will talk more about the similarities and differences between GRACE and AOHIS on the next slide.
So as Vardhni touched on in the last slide, we chose to use the AOHIS model dataset with the GRACE dataset in our project because both the GRACE and AOHIS datasets are showing Earth's gravitational potential expressed as spherical harmonic coefficients, which, as Ethan talked about earlier, give information about water mass variability. Both the datasets also have very similar spatial resolutions. So the main differences to keep in mind is that AOHIS is a model dataset, which means it was created by scientists, and the GRACE dataset is real satellite data. AOHIS is available from 1995 to 2006, and the GRACE mission ran from 2002 to 2017. GRACE follow-on mission ran from 2018 to the present. So now that we've introduced the data, Naina will get into the work we did this summer.
Now that my teammates have explained our datasets and what AOHIS and GRACE are, I'm going to explain what machine learning is and how machine learning is used to help scientists understand natural phenomena from all around the world. What is machine learning? Well, machine learning is a subset of AI where a system can learn from data and modify itself as it gains more experience. The computer programs focus on adapting to new data and algorithms to try and copy the way that humans learn, but without needing human interference, meaning that like a human brain, as they learn new things, their accuracy gradually improves. Why are we using machine learning? What if we use machine learning to help analyze and process satellite data more rapidly? There's often a delay between when satellites collect data and when the maps are produced, and this makes it difficult for crisis assistance and being able to see trends immediately. With machine learning, maps like the one below that Ethan had previously explained can be processed more efficiently and used more effectively.
So before we talk about our experiments from last year, let's walk through the steps to using a neural network. The first stage is called training. And this is where you give the neural network a data set that has known inputs and known outputs. And the network adjusts its weights and parameters to maximize the likelihood of the outputs matching the known input. For the testing stage, the parameters have been fixed from the training stage. And this time, you give it data that again has known inputs and known outputs, but this time it evaluates the accuracy. For actual use, you give the neural network new data that it hasn't already have the known outputs, and after it's been trained and tested. For the training stage, we will be using the AOHIS dataset, and for the testing stage, we'll be using the GRACE dataset.
Thanks to the pandemic, 3 of our team members were able to return this year, allowing us to really continue our work from last year. Throughout last summer, we developed a machine learning algorithm with the goal of sorting the GRACE data by month. We used the AOHIS data for training and the GRACE data for testing in order to see what we could learn about the GRACE data from the AOHIS data. We used 5 different regions: Australia, the Middle East, Greenland, South America, and a smaller subset, the Amazon. We chose these locations as they had strong signals, yet they were different and unique of one another. As you can see on the right side of the screen, we have plots for each of the regions, and they display accuracies after training in purple and accuracies after testing in blue. We can see that the testing accuracies are generally lower, and this is due to the fact that the weights are optimized for training, not testing. We do have slight overfitting, seen by the significant gap between testing and training, where the network is somewhat memorizing the training data. But these results are still better than randomly sorting the data by month, which would yield about 8% accuracy. From our experiments last year, we are able to answer yes to our question of can a machine learning algorithm be used to learn anything about hydrological signals seen in the GRACE data. This year, we used convolutional neural networks, or CNNs, primarily in our machine learning part of the project, and as inputs, we used images of grid maps, such as the one seen on the left side of the screen. This is an example of South America, and these inputs are in the form of RGB pixel values. The goal of our neural network was to match images of grid maps to the month that they were taken. So looking at this from a more general view, convolutional neural networks are composed of convolutional layers, which help pick up on features of the image. Then through a process of pooling, these features are resized as the convolutional neural network runs. Eventually, this leads to outputs of matching the images of grid maps to the corresponding month. The neural network does this by creating a probability of the likelihood that the image corresponds to each month. The highest probability is considered the accurate output by the neural network.
While we're still working towards the ultimate goal of understanding whether machine learning methods can be used to identify changes in groundwater storage using GRACE satellite data, this summer we focused specifically on answering the question, does the input data type have an impact on the effectiveness of our machine learning algorithm? So last year we worked with images of equivalent water thickness data, and this year we experimented on feeding our network matrices of equivalent water thickness values, which Lindsay will talk about.
So this year, like Anjali said, instead of feeding our neural network RGB pixel values, we're feeding it matrices of equivalent water thickness in centimeters. The architecture is still almost identical, and we're still sorting the data by month, so this allows us to see whether the input type alters the results.
After we determined and developed our input data, we had to consider the structure of our model known as the convolutional neural network architecture. The CNN architectures are composed of various parameters, which affect the architecture and can change the accuracy by varying degrees. Therefore, one of the main extensive experiments that were conducted was tweaking and testing the values of these parameters, such as pooling size, number of epochs, and many more that are not listed here, to develop an effective model that produces acceptable accuracies necessary to develop conclusions.
After conducting all of our experiments, these are our results. Starting with South America, both the images and matrices reached a training accuracy of 100%, although the matrices test reached a higher testing accuracy than that of the image test by about 8%. South America has such a high training accuracy because it has such a large signal, and because the AOHIS data is very similar to the GRACE data for this region. This can be seen on the plot at the bottom of the screen, where the blue line representing the GRACE data and the red line representing the AOHIS data lie almost on top of each other. We also observed a more specific region of South America, the Amazon. The matrices for the Amazon had a higher testing accuracy of 65% compared to the image testing accuracy of 58%. But they are comparable because the training accuracy of the image is slightly higher than that of the matrix.
Both Australia and the Middle East were the regions with the largest increase in testing accuracies between the two input types. The matrices gained close to or more than a 10% increase in testing, with Australia having a 22.44% increase and the Middle East having an 8.34% increase, indicating that the input data does actually have an effect on the accuracies.
And the last region we looked at was Greenland. So as you can see, the image results and the matrix results were pretty comparable, both having testing accuracies around 20%, which is what we averaged for all of our tests for Greenland. What is interesting to notice is that these testing accuracies are much lower than all of the other regions. And it's due to the fact that
there's a downward linear trend caused by ice melting and leaving the region that we can see in the equivalent water thickness plot at the bottom. And also the difference in relative means between the AOHIS and GRACE data is so great that learning really isn't happening within our network, which is why we see such low testing accuracies.
Ultimately, we found that in nearly all of the regions we tested, using matrices yielded results that were as good or better than the image data results. In both the matrix results and the image data results from the regions Australia, South America, the Amazon, and the Middle East, training accuracies were in the mid to high 90s and even up to 100. Testing accuracies were more varied between the matrix and image results, as the testing accuracies for matrices were frequently 5 to 10% higher than the image training accuracies. This is significant because the testing accuracy correlates to how well the network generalizes. Higher testing accuracies mean that the network is better at learning from the given data and applying what it has learned to data that it is not familiar with during the testing stage. However, our results for the region Greenland were inconclusive because learning did not occur. As Anjali explained earlier, Greenland's low testing accuracy, which hovered at around 19 to 22%, can be attributed to a downward linear trend caused by melting ice leaving the region. It is also important to note that the training times for matrices were much lower than the training times for images. This can be attributed to the relative sizes of input of the matrices and images because, while the images are represented as tensors with a depth of 3, matrix data is only 2-dimensional and has no depth, which means that the input for the matrix data is at least 3 times smaller than the input for the image data. Based on these results, we are interested in learning more about how changing the input data type impacts the training and testing accuracies of different kinds of experiments beyond just sorting grid maps into months.
Now that we've concluded the results section of our presentation, we're going to get into some reflections from this summer. For me, having the opportunity to learn and utilize machine learning has been amazing. The coding opportunities are limited where I live, and being able to develop skills that I can use in a career has been immensely beneficial. I have also gotten better at presenting my work in a clear and concise manner, which is very important for any number of situations.
Participating in this program gave me the opportunity to meet and work in a team with new people. Together, we all worked to overcome problems, whether it was errors in our code or questions about what we were learning. Over the summer, I have gained so much more confidence in myself and learned so many new things, like what neural networks are, how to run machine learning tests, changing architectures, and much more about the data collected by GRACE.
Before SEAS, I had an interest in environmental science, but I also knew my strengths were in STEM. And this program really showed me how I can combine both my interests and my skills, and inspired me to pursue computer science in college with an environmental point of view.
SEAS has been an absolutely incredible experience and has opened my eyes to a world of science that I had not previously been exposed to. Working with GRACE data has allowed me to learn more about how Earth science intersects with other fields of science, such as machine learning and Python, 2 subjects that I've always been interested in, but never really had the chance to work with directly. Now that SEAS has come to an end, I feel that I have gained confidence in working with unfamiliar subjects and sharing my thoughts in a team setting.
Prior to joining SEAS, I always thought about getting into machine learning, but I didn't know what to learn or where to start. However, SEAS has provided that gateway to gain a deeper understanding about machine learning and STEM. SEAS is one of the programs that give high-level educational opportunities to young high school students, where we get to use real data to research and develop conclusions about our experiments. I thoroughly enjoyed learning about the GRACE mission and how machine learning can be applied to environmental data. And like Anjali, also consider going into computer science for college.
SEAS has taught me how to communicate better with my peers, and I have much more confidence in my presentation skills as well. On the technical side, I have a much deeper understanding of machine learning, and I can understand the terminology and what the vocabulary means. Also, I've learned so much about the GRACE satellite and what the data shows about our world and how it changes over time.
We would like to extend a special thanks to Ms. Baggio, Ms. Miller, and our amazing mentor, Corinne Vassallo, as well as the entire SEAS program. Any questions?
So I invite the GRACE team to please turn on your cameras and your microphones. We have several questions for you. The first is, how would you explain spherical harmonic coefficients to a non-scientist?
I can take that one. That's a really great question because they can be a bit confusing. But to a non-scientist, I would start by explaining a concept called Fourier series, which basically says that any function can be modeled by an infinite sum of sines and cosines, and then expand on that by saying that spherical harmonics build on this idea because they're numbers that weight sine and cosine like functions to represent three-dimensional or spherical shapes.
Are the GRACE and AOHIS data sets available for general use?
Yes, they are. So the AOHIS data is available on the ESA site or the European Space Agency website, and GRACE is on the CSR website, and it comes in various forms.
How long does it take for machine learning to exceed the abilities of human learning?
In the end, we actually don't know because this depends on a lot of factors such as the research of machine learning and how our physical processes can keep up with this machine learning. But more pertaining to our project, we aren't actually trying to exceed human learning. We are trying to speed up human-driven processes by making them more data-driven.
Were there any regions that AOHIS was not able to model accurately? And if not, do you know what it was about the area that made it more difficult?
So one area that we did see a major discrepancy between training and testing accuracies was Greenland. And this is due to a lot of ice melt where water is leaving the region at a very fast rate. So AOHIS and GRACE data don't overlap in the same manner. So the two data sets weren't able to, AOHIS wasn't able to model GRACE very effectively for that region.
The next question, could this technique be applied to other planets? Like if we had the right kind of satellite around Mars, could we map water on Mars?
Yes, once again, that's a really great question. And I don't see why not, except it is important to note that if we were to do this on other planets, it wouldn't necessarily be tracking water change, but instead mass change.
And what software did you use for the convolutional neural networks? PyTorch and TensorFlow are both considered good options. Do you have advice for others?
So for convolutional neural networks, we use TensorFlow, and we don't have any advice for other networks as we didn't use any of those libraries outside of Python.
What is the difference in accuracy so big for Greenland?
So the difference in testing and training accuracies is really big in Greenland because the AOHIS and GRACE data have really different relative means. So like when we train our network with the AOHIS, it's not really learning properly and it can't apply its learning to the GRACE data.
And our next question is, why do you think that the matrices performed better than RGB images?
So we didn't really go too much into why the matrices were better than the RGB images, but it's probably because the signals are more clear in equivalent water thickness space than the RGB space for the algorithm.
And our last question is, do you have any ideas on how to overcome overfitting that you would like to test in the future?
Yes, so our goal to overcome overfitting is to actually combine the GRACE and AOHIS data sets for training. And so we wouldn't just use the AOHIS data. So this would allow us to augment the GRACE data with model data, which hopefully with several tests would maybe allow us to overcome this overfitting.
Great job to the GRACE team. We appreciate all of the science that you conducted and your contributions to the GRACE mission. So we will have about a 25-minute break. SEAS interns completed an online Earth and Space Science course as part of their project, in addition to a Python coding course for those that wish to participate. We invite you to watch the video highlights featuring data produced by the students during this course during our break. We will also share a video of SEAS alumni sharing their experience when they participated in the SEAS program. We will begin the next session at 2:30 Central Time. Thanks, and come back when you're through.
My name is Saneri Patel.
My name is Aiden McLaughlin.
My name is Anavi Opal.
I'm Keegan Fong. I'm from Memphis, Tennessee.
From San Jose, California.
I'm from Palmer, Alaska.
And I'm from Seattle, Washington.
From Montclair, New Jersey. And this summer I became a NASA scientist.
And this summer I became a NASA aerospace engineer.
I became a NASA researcher.
I became a NASA astronomer.
My name is Nikki from Columbia, South Carolina. This summer I became a NASA researcher.
I decided to apply because I've never had the opportunity to learn about space exploration or astronomy other than from a book or from a classroom setting, but I thought that this internship would give me the opportunity to have a more hands-on experience.
And my school didn't offer a lot of opportunities to learn about aerospace or astronomy, so I thought that this internship was a good way to learn more about the subject area that I wanted to pursue later in life.
And I decided to apply because the level and the depth of the research being done in SEAS was unparalleled by any other program.
To actually have the opportunity to work with NASA scientists and professionals in the STEM industry, it seemed way too good to be true.
After working alongside scientists and engineers at the Center for Space Research and listening to dozens of professionals share about their jobs, I now have a better understanding of what my career might look like someday and of the steps I need to take to get there.
The internship helped me prepare for my future career by allowing us to work together in a team to complete a project with both time and resource constraints. We engaged in serious debugging efforts involved with real-world programming, cultivating patience and attention to detail.
It was unlike any other team project I had ever been a part of because every one of us was so passionate and excited about what we were working on.
I'm really glad that I was able to have this experience before my senior year because I don't know what position I would be in if it weren't for this internship.
And I feel that I have all the tools that are necessary now for pursuing a job at NASA in the future.
So going into this program, I honestly wasn't entirely sure what I wanted to do. Definitely coming out of this program, I know that I want to be an aerospace engineer. I want to work in the aerospace industry. I want to be a part of what I was able to experience with the program. And so that guidance specifically is something that I have to thank the internship for, because without the program, I would still probably be lost trying to figure out what I want to do as a career and major in college.
But it has also made me consider other careers relating to space, such as engineering and planetary science. I most likely wouldn't have considered these other options if it hadn't been for the experiences that I had at SEAS.
This internship has really reinforced how I see my future career in that it has provided me the confidence to continue with computer science.
SEAS has reinforced the idea that I want to work with NASA, and it also told me that it's possible. Before SEAS, I thought I was overreaching by thinking I'd be able to work with the great minds at NASA, but after SEAS, I know that I can do it because I have done it and it was amazing and I'd love to do it again.
The SEAS internship led me to realize that my dreams of someday working for NASA are much more within reach than I had once thought. I don't have to be a genius to work for NASA. I just have to be dedicated and willing to work hard.
They showed me how doing what you love can change the world.
NASA SEAS helped me become a software engineer.
They really helped me gain my confidence in the STEM field and made me realize that I could translate my passion for science into a successful career.
The STEM Enhancement in Earth and Space Science Internship is an intensive, nationally competitive program for 10th and 11th grade students. SEAS, a partnership between the University of Texas at Austin, Texas Space Grant, and NASA, provides students the opportunity to conduct authentic research while being mentored by NASA's subject matter experts.
SEAS helped me solidify my desire to work in the space industry.
It was so surreal to have the opportunity to meet NASA scientists and engineers, as well as meet other students as passionate about STEM as I was.
SEAS helped me improve my teamwork and collaboration skills by placing me in a professional environment early in my career.
90% of SEAS alumni have gone on to major in STEM in college, preparing them for careers in science, technology, engineering, and math.
SEAS gave me the confidence to pursue further research opportunities in science and technology.
The SEAS program has helped me become a better researcher and scientist. I use the skills that I learned within the SEAS program that summer every day in my current field of biomedical sciences.
Former SEAS interns have gone on to become Back to Space student ambassadors, presented at professional conferences, won national competitions, attended Ivy League schools, received scholarships, and interned with companies such as Google and NASA.
SEAS has helped me get into college and land internships.
I first heard of NASA's Pathways Co-op program on the SEAS tour, and I'm happy to say that I started my first term as a NASA co-op this spring.
The SEAS program in 2016 was my first experience with programming or any sort of computer science, and now I am studying computer science as a junior at Vanderbilt.
I helped start an astronomy club at my school after SEAS. SEAS helped me become more ambitious and believe in myself more, which I'm always thankful for.
These amazing students attribute their experience and their growth to participating in the SEAS program. Here's an example of how students have been affected by this nationally recognized internship.
I always cite SEAS as the program that put me on the path that I'm on now.
And I think it was an experience that I would never forget.
But best of all, SEAS reminded me that there's so much more for me to learn. And I was left feeling excited for what discoveries the future will hold.
Overall, the Texas Space Grant Consortium through NASA and the SEAS program has helped me become a more confident and better student. And through the amazing network that SEAS helped me develop, that has translated into me becoming a better person and contributor to the world of STEM.
First of all, I want to share with all of the interns that I cannot wait to see what your future path holds. And also we need to give a big shout out and thank you to Teresa, Sarah, and Asha for the monumental task of weeding through, scoring, collecting all of the data from all of the interns for the Earth and Space Science course. We appreciate you and thank you so much for doing that project. So our next project is aerospace engineering. We want to give a special thanks to their mentor, Dr. Wallace Fowler, for his leadership and guidance. The SEAS 2021 Aerospace Engineering team designed a satellite and mission to monitor one or more aspects of the Earth's environment. The team chose environmental aspects to be monitored, defined the satellite's orbit, identified the sensors that are carried on the satellite, specified the satellite's launch site, and chose the rocket to be used for the launch. Prior to their mission design, students learned about current Earth orbiting satellites, selected environmental phenomena to be studied, researched sensors, and proposed conceptual designs with their teammates. Please join me in welcoming the aerospace engineering team and their project InsoSat.
Hello everyone, we're the NASA SEAS Aerospace team and we have designed InsoSat, which stands for El Niño Southern Oscillation Satellite. Here are all the members of the aerospace engineering team.
My name is Catherine Clay, and I am from San Antonio, Texas.
Hi, my name is Jordan Cochran, and I'm from Columbia, South Carolina.
My name is Kyla Hunter, and I'm from Flowood, Mississippi.
Hi, my name is Pragadeshwar Kalatishran, and I'm from Bridgewater, New Jersey.
Hi, my name is Mary Lay, and I am from Portland, Oregon.
I'm Aparna Majetti, and I'm from Austin, Texas.
Hi, my name is Ritvik Radigari, and I'm from Ashburn, Virginia.
Hello, my name is Jacob Rivera as part of the SEAS Aerospace Engineering team. I go to City Honor.
Hi, my name is Giovanni Vasquez, and I'm from Charlottesville, Virginia.
Our broad goal is to research global warming and climate change by monitoring El Niño, also known as El Niño Southern Oscillations, or ENSO, which is an irregularly occurring natural phenomenon that mainly occurs in the Pacific Ocean every 2 to 7 years. This will be done by monitoring a variety of environmental factors, including sea level rise, tropical storms, and greenhouse gas emissions.
El Niño, also known as El Niño Southern Oscillation, or ENSO, is a natural phenomenon that mainly occurs in the Pacific Ocean every 2 to 7 years, lasting 9 to 12 months, and can affect weather worldwide. The ENSO cycle is made up of El Niño and La Niña, which are opposite phases, and the ENSO cycle is a scientific term that describes the fluctuations in temperature between ocean and atmosphere in the east-central equatorial Pacific. Scientists today can only predict El Niño 6 months to a year before it takes place. The effects of this weather phenomenon include severe drought, flooding, and etc. In North America, El Niño often results in warmer than average temperatures over western and central Canada, and over the western and northern U.S. In addition, drier than average conditions can be expected in Ohio Valley and the Pacific Northwest. Some of the weather effects include landslides, storms, flooding in California, and even crop damage. There have been increased wildfires in southern Mexico and Central America. The benefit to studying El Niño weather phenomenon is to understand the global climate system, since El Niño has such a large ripple effect. Due to greenhouse gas emissions, extreme El Niño events may increase more frequently. For example, global warming can cause El Niño events to shift eastward along the equator in the Pacific Ocean. This was shown through the 2015 through 2016 Super El Niño. During this time, more than 60 million people were affected, and more than $3.6 billion went into helping the humanitarian response. These changing weather patterns can have disastrous effects on agriculture, ecosystems, air quality, and much more.
El Niño was first recorded in 1525 by Spanish conquistador Francisco Pizarro, when he noticed abnormal desert rainfall in northern Peru. The weather phenomenon eventually received its name during the 19th century as fishermen in Peru observed the way the warm water flowed south during Christmas time. El Niño is Spanish for the boy child, or the Christ child, and is also referred to as El Niño Southern Oscillation, also known as ENSO. The Southern Oscillation originated from Sir Gilbert Walker in the 1930s, as he noticed the pattern of interannual change in the tropical atmosphere. The most recent ENSO was in 2018 to 2019, but the strongest years recorded were 1982, 1997, and 2015. The 1982 El Niño brought about the rise of the bubonic plague in New Mexico, abnormal temperature rise in Alaska and Canada, and a shift in Earth's angular momentum, which increased the day's length by 0.2 milliseconds in late January. The 1997 El Niño left 16% of the world's breeze systems destroyed, increased the temperature in the air by 1.5 degrees Celsius. During the water season, California saw record rainfalls, and Indonesia marked the year to be one of its worst droughts in its history. The 2015 El Niño produced widespread drought across the globe, along with strong floods. Despite the predictions that ENSO would get weaker over time, it instead continued to get stronger throughout the year. In 2015, ocean temperatures rose more than 2 degrees Celsius in the Niño 3.4 region. The phenomenon also triggered disease outbreaks such as hantavirus, cholera, and dengue fever in Colorado, Tanzania, and Brazil. Indonesia is typically known to be one of the rainiest places in the world. However, during the 2015 El Niño, drought led to large fires and produced a disproportionate amount of smoke. The aftermath of the fires lowered the air quality for Indonesia and its surrounding areas. The 1998 ENSO produced large amounts of rain in North and South America, along with dry weather throughout the rest of the world. The ocean temperature rose about 3.6 degrees Fahrenheit during the fall. As you can see in the picture, landslides, drought, rain, and famine were the aftermath effects of this weather phenomenon. Nicaragua also faced a large drought because the average percent of rain dropped 75%, also affecting the farmers and the economy. This caused the production of meat and dairy to fall as the prices for them continued to rise. In 2016, more than 31 million people in China were affected by floods triggered by El Niño. It was recorded to be the worst flood since 1998, submerging 6.7 million acres of cropland and destroying major farms.
Current conditions. Despite the onset of an El Niño in the UK Met Office, scientists forecasting a cooler year in the Pacific Northwest. Oregon saw record-breaking high temperatures and alarming increased drought conditions as a result of greenhouse gas influence. Researchers from the World Weather Attribution, peer-reviewed, write that the observed temperatures were so extreme that they lie far outside the range of historically observed temperatures. A new analysis found that these conditions would have been virtually impossible without human-caused climate change. This past heat wave killed 116 people in Oregon. Multnomah County makes up our Oregon's highest death toll, with 54 confirmed and 17 suspected hypothermia deaths. And for context, prior to the heat wave, the county had just 2 deaths from heat in the past 20 years. With an El Nino on the rise, conditions will only become more severe. Given time constraints and current local housing under-equipped for heat, such weather conditions prove to be deadly, especially to the most vulnerable population experiencing homelessness. Mission overview. The mission itself is to design an Earth-observing satellite with consideration to several factors, starting with a picture on the top right that compares the movement of warm and cold water in a normal year and in an El Nino year. El Nino Southern Oscillation is the warming of the ocean surface or above average sea surface temperatures in the central and eastern tropical Pacific Ocean. This warming causes a shift in the atmospheric circulation, with rainfall becoming reduced over Indonesia, India, and Australia, while rainfall and tropical cyclone formation increases over the tropical Pacific Ocean. The low-level surface trade winds, which normally blow from east to west along the equator, either weaken or start blowing from the other direction. The picture below on the right shows a country in East Africa facing the devastating effects of the El Nino weather phenomenon. Several East African nations reported much heavier rainfall this rainy season, which many experts say is due to changing weather patterns. The mission designed by our team covers research and understanding of the ENSO cycle and the development of a satellite that monitors this weather phenomenon. The satellite has been designed with consideration to the launch, the orbit, and the data that is monitored, as you can see from the picture of the ground tracks, a sketch of the satellite, and a launch rocket.
We created a list of mission requirements for our mission, which outlines what the satellite and its instruments shall do while the satellite is in orbit around the Earth. These requirements include observing the El Nino phenomenon, covering plus or minus 60 degrees in latitude, monitoring sea level changes, reporting tropical storms, monitoring atmospheric carbon dioxide, having a design lifespan of 15 years, and having a launch mass of no more than 2,300 kilograms. Some additional requirements pertain to the specifics of the mission, such as the altitude at which the satellite will orbit at, where the satellite will launch from, and the amount of power the satellite will generate by the end of its life. These requirements ensure that the satellite is able to obtain the appropriate data for the planned amount of time, and that it is able to transmit this data down to Earth so that it could aid in the research of El Nino. This is a conceptual model of the ENSOSat, which was created using computer-aided design. The body of the satellite measures 3 meters by 2 meters, and the solar panels on both sides are able to rotate so as to constantly face the sun. As can be seen in this model, the Poseidon 3 radar altimeter always points nadir, or downwards towards the Earth. An additional instrument that can be seen is the Tanso FTS sensor.
We plan to launch our rocket from Kennedy Space Center in Florida utilizing a SpaceX Falcon 9 rocket. Our satellite will be launched into an orbit with an altitude of 800 kilometers, an inclination of 60 degrees, and a period of about 101 minutes. Our satellite will have a payload mass of 633 kilograms and a total mass of 2,274 kilograms. At the end of its use, we plan to deorbit our rocket using an onboard booster.
Using our satellite, we will monitor sea level rise, greenhouse gases, and weather. To monitor sea level rise, we will be using the Poseidon 3B radar altimeter on the Jason 3 satellite. Jason 3 is an international mission which was launched on January 17, 2016 in Vandenberg to gain more understanding on ocean circulation and climate change. It is currently active and makes detailed measurements on the height of the ocean surface, which provides information on changes in sea level and circulation. Tracking sea level using altimeter data can help predict El Nino, which gives rise to warmer sea temperatures in the eastern tropics, causing higher sea levels. Poseidon 3B is a radar altimeter that calculates aspects of the ocean, including wave height and ocean surface current velocity, by emitting a radar beam that gets reflected from the Earth's surface and back to the antenna. It also tracks ocean topography, sea level rise, and gravity field through 2 frequencies at 5.3 and 13.58 gigahertz. Its radar antenna has a diameter of 1.2 meters, which samples at 30 kilometer intervals along track. The average data rate for this instrument is 37 kilobits per second with a mass of 70 kilograms and a power of 78 watts. This image captures the sea level rise from December 1997 and 2015 from the Jason 3 satellite. The red area represents higher sea levels, while the purple regions represent lower sea levels. Our next environmental factor that we will monitor are the greenhouse gases. To monitor greenhouse gases, we will be using TANSO FTS2, which stands for Thermal and Near-Infrared Sensor for Carbon Observation, Fourier Transform Spectrometer 2. This is used on the GOSAT-2 satellite to measure greenhouse gas concentrations, specifically carbon dioxide, methane, and carbon monoxide with extremely high accuracy. The GOSAT-2 was a follow on the GOSAT satellite, which was a greenhouse gas observing satellite originally launched on January 23, 2009, as a joint project between the Japan Aerospace Exploration Agency and the National Institute of Environmental Studies. This satellite's primary mission is to measure carbon dioxide and methane in the Earth's atmosphere using TANSO FTS2. This instrument allows scientists to discriminate between natural and man-made emissions by measuring shortwave infrared sunlight reflecting from the ocean. It has a mass of 255 kilograms and a power of 187.2 watts.
Our final factor to monitor is weather, and the ABI will assist us in this. The ABI, or the Advanced Baseline Imager, observes Earth's surface, atmosphere, and cloud cover, but more precisely, its oceans and weather. It has a multi-channel passive imagery radiometer designed to record and provide variable error imagery and radiometric information. This is also a primary instrument of the Geostationary Operational Environmental Satellite, or series. It has a mass of 338 kilograms and 450 watts in power.
This graphic shows the makeup of our satellite's mass and the percentage of each separate subsystem. The wiring, thermal, and telemetry tracking and control subsystems each account for about 4% and 90 kilograms of our satellite's total mass. The altitude and orbit control subsystem makes up 7%, or about 158 kilograms of the satellite's total mass. This subsystem will help ensure that our satellite is always nadir pointing. The propulsion system will aid in maneuvering the satellite and will be used to deorbit the satellite at its end of use. It accounts for about 12% and 286 kilograms of the satellite's total mass. The structure subsystem of our satellite has a mass of 407 kilograms and is 18% of the satellite's total mass. The second largest subsystem on our satellite is the power subsystem. It includes solar panels and battery packs that will power our satellite. It has a mass of about 520 kilograms and is 23% of the satellite's total mass. The largest subsystem is the satellite's payload. It is 28% and 633 kilograms of the satellite's total mass. In the center of the graphic, the total mass of our satellite is displayed.
Power is necessary in any satellite, and this is our power system. Our satellite needs 905 watts of power, and for times when light is scarce, ENSOSat will have a battery with a capacity of 1.7 kilowatt hours. To accommodate for charging the battery while powering the satellite, ENSOSat will have 10 square meters of solar panels.
To dispose of our satellite, we will implement a two-burn Hotman transfer utilizing a cold gas powered booster. The Hotman transfer will deorbit our satellite to an altitude of 146 kilometers, where it will eventually burn up due to atmospheric drag. The booster will likely be powered by CO2, similar to those used on the Grace mission. No longer functioning satellites are left in orbit, which serves as space debris. This negatively affects the planet as well as space exploration by potentially leading to in-space collisions. Additionally, large enough pieces of space debris left in a low orbit can strike the planet's surface.
Some of the challenges that we had to overcome during our time at this internship really included working with new technologies that we had never seen before, like TK Solver, which is an orbital mechanics calculation software. Additionally, we had to learn new fields of science, such as orbital mechanics, because we're working with satellites, which is something that none of us had actually worked with before. So it was really interesting to get that group learning experience. Additionally, we had to grapple with advocating for our team and also coordinating our team. So coordinating schedules, we're all across the country, so it's very difficult to find times that work for all of us, but I think that my team did a very good job of this. And advocating for our skills and our abilities to scientific journals, which is something that we're doing, which sort of goes above and beyond the standard project. So yeah, so those are some of the challenges that we face as a team, but I think we did a very good job, and I think all of the team members left with a better understanding of what it means to be a productive member of a research team.
Furthermore, our team was excited to work in a collaborative research environment with other like-minded high schoolers who have similar goals and aspirations. Finally, I would like to say thank you. We would like to express our deepest gratitude to Dr. Wallace Fowler for his guidance, knowledge, and unwavering support in our journey to designing our satellite. We would also like to thank Dr. Teresa Howard, Selena Miller, and the SEAS staff for providing this unique opportunity. Thank you.
So we have several questions for the aerospace engineering team. If you would turn on your cameras and your microphones. Our first question is, how did you choose your final mission requirements?
So I can answer that question. So for the requirements, they were largely inspired by the official NASA mission requirements for the GRACE FO satellite. So basically what we did was we took a look at the document about the GRACE FO, and then we basically shortlisted what requirements do we want in our satellite that's applicable for studying El Nino. And those requirements include things like where, like what the altitude will be, where it will launch from, and things like that.
How did your research on historical INSO conditions contribute to your mission design?
So while I was researching, oh, go ahead.
Okay, I was gonna say, while we were researching El Nino, we saw where it affected places worldwide, and that sort of determines where we wanted our satellite to travel based on its latitude and longitude, based on the places that El Nino essentially affected.
So while I was researching about El Nino, I discovered a 2019 study from scientists in China and the US where they examined about 33 different El Ninos from back to 1901, and then discovered that every El Nino after the 1970s moved further out west in the Pacific Ocean, which can lead to more intense droughts in places like India and Australia. And if the ocean temperatures were continued to rise, that could lead to more intense El Ninos in the future.
A few of the things that we were looking at when we were determining some of the satellite instruments were also based off of what are the different things that cause El Ninos. So like any of the carbon monitoring or some of the ocean monitoring that we had to do was kind of essential. And we were finding this out as we were doing research on El Ninos. So it was kind of integral to our instrument selection.
So how did you decide or determine the mass of your satellite?
Right, so we initially started by looking at a number of instruments, and once we narrowed down the list, we were able to research those instruments further and look at their specifications on other satellites. So we had their volume and their mass, and that helped us determine the final numbers.
How long would you expect your satellite to be operational?
We say that our satellite will be operational for 15 years.
Why is planning for a satellite end of life so important?
I would say planning this out is important because at the satellite's end of life, if you just discard it as space debris, it can become problems for future satellites, and it can run into them, which would be a major problem. So it'd be better to burn it off into the Earth's atmosphere instead of leaving it out in space.
Also, another mention is that space debris is also like already a really big problem in space, and it's a big challenge, so we better not escalate it.
So how do you make sure the entire satellite would burn up and doesn't turn into space debris when it re-enters?
So the Tubern-Hoffman transfer pushes the satellite lower into the atmosphere, where it would experience atmospheric drag, and over time it would burn up due to the drag.
So the question, well, first of all, this is a great satellite idea. Does your group have any plan to make a formal proposal?
So our group is planning to submit our formal satellite proposal to a research journal so that the proposal can be published in a research journal.
And what challenges did you face working virtually?
Part of our challenges just were coordinating times for meetings because we're kind of all over the country in different time zones. We had some learning curve with some of the tools that we were using. For example, TK Solver. It was a bit of a learning curve since we were all kind of new to orbital mechanics as well as the software. And as well as just creating like some of the CAD things. So we had a few like minor roadblocks, but nothing that, set us back overall.
So this is a personal question for me as a follow-on. So do you think it would be helpful to work with students in your same time zone on future projects?
I think it would help, but it wouldn't really mitigate the problem since a lot of us also have other things going on. So either way, we would face the same challenges.
And I would like to add on to that. It would definitely be hard, but also seeing other people from different parts of the countries and different ideas that they bring to the table is also very important, and it helped us out a lot.
What was the most surprising piece of data that you came across during your research?
I can tackle this one. And so one of the most surprising pieces of data I found was that scientists originally predicted in 2020 that in the summer of 2021, the Pacific Northwest area would be seeing like lower summer temperatures because of an El Nino as opposed to an El Nino. But instead we saw a major heat wave, and that is a major contributing factor is the global warming and the carbon emissions, which is why it led us to study for our satellite.
Do you believe that reversing or slowing down the effects of global warming would have an impact on El Nino?
Yes, it definitely has already had an impact on El Nino. That was actually in one of the slides. It was El Nino and climate change, and it showed that greenhouse gas emissions had made the El Nino events more extreme.
And did your group look at the effects of varying the orbit altitude or inclination of this satellite?
Right. So when we were initially choosing our orbit and its inclination and its altitude, we looked at a variety of different possibilities, and we ultimately decided that the ones we chose were best suited for our scenario since it would allow us to cover a large portion of the planet and get accurate data since the sensors are limited to how far they can see.
Well, y'all have done an amazing job. Your research is important to our environment, and I think the skills you learned with Dr. Fowler will carry you on in your future. So thank you all for your presentation today. Our next project group is the NASA Robotics, an introduction to coding, robotics, and physical computing. We want to give a special thanks to their project mentors, Sherelle Webb and Gerald Giolito, for their expertise and guidance. We have 5 team presentations. The robotics interns learned about coding basics, programming, and robotics. Student used Raspberry Pi and developed technologies for the future while investigating wearable technology, robotics, and the importance of robotics in space exploration. So should we have time at the end of their presentations, we will hold all questions to the end. So our first robotics presentation is Hike Alert.
Hi, my name is Josh Petroza, and I go to Esperanza College Prep in East Los Angeles, California. And over the summer, I was part of the SEA's NASA Robotics group, and my project is called Hike Alert. For our project, we were asked to create a wearable device that could possibly solve a problem we see in society. Some examples of wearable devices in society are smartwatches, smartphones, AR or even VR goggles, etc. Keeping that in mind, for my project, I wanted to help find a way to prevent people from being endangered when they go hiking. I believe this is important to talk about and to find a solution because on the news, there are cases where people have gone missing for days because they've lost communication with others so they can't call for help. This is why I believe that a smartphone shouldn't be your only device that you should use to call for help, because what if something goes wrong with your phone where you lose signal or you lose battery life, or even if it's just broken from your hike? This is where my device comes in. My device is called Hike Alert, and here's how it works. You enter the park or the mountain and you enter the code for that area. Or hopefully in the future it automatically connects. So the device's purpose is to make sure that you're safe. So every 30 minutes a red light will flash. You have within 5 minutes to press the button on the device once in order to deactivate the light. If you don't, a rescue team will be sent to your location. Someone might ask, what if I don't have 30 minutes to spare and I just got bit by an animal or I fell? Then all you need to do is press the device's button 3 times and it will send the same rescue team over to your location as soon as possible. In the interior, I used a button, a red LED light, and hopefully in the future I can use the trackers to help find the person's location quicker, and a speaker just in case communication does need to occur. Note that the exterior of the device is pretty lightweight, so you shouldn't have any trouble carrying it on your hike because it could be worn as a keychain or on your wrist, as seen in the images below. In the future, I believe that this is how the rescue team's screens should look like, just so that it's easier to find the person in danger. Hopefully, this device could be implemented in every park or mountain for the safety of the people. I'd like to take a moment to thank the SEAS program, my project mentors, Ms. Sherelle Webb and Mr. Gerald, for helping me create a clear understanding of what it's like to work in STEM so that I can pursue it later in life with higher education. This internship did have some challenges, like being completely virtual, so there wasn't as much hands-on assistance and all the time constraints to complete the project, but I believe what made up for it was my project mentors' quick help for troubleshooting anything that went wrong. Next year, I believe that I will study STEM 100% because of this program, so thank you.
Our next robotics presentation is Pi Hole, a black hole for internet advertisements.
Today I will be presenting my project. I am on the NASA Robotics team, and let's get started. The project I chose to do today is Pi Hole. On the left in purple, you can see those were my interns that were in my class. And on the left in blue, you could see my mentors that really helped me a lot through this process. Background and goals. The project I decided to do was an ad blocker, also known as Pi-hole. It is the most efficient way to block ad networks since it works at a DNS level, which means it does not affect the network performance and it can actually improve it, considering that some ads can slow down the loading time for the websites or app. My main goal was to eliminate all ads on my network. And I really thought this project was interesting because, I would be watching a show or something on YouTube and a really annoying ad would come up. And I just want to get back to the show or the thing I was watching. So I thought this was very helpful, very useful, very exciting, and I knew my family would enjoy it too. Research. It took me a lot of research because it was my first time dealing with a Raspberry Pi. I had to watch many YouTube videos on how to set it up before I could start the real project. Within the time to get started on the real project, I had to do a little more research on how to download different softwares and learn different codes. I do a lot of coding at home and I do a lot of fixing at home, but this was completely new to me. I've never seen a Raspberry Pi. I've never dealt with a Raspberry Pi before, so this was all very new to me. I had to do a little bit of my own research before getting started. The results. The results were great. I had fun with my first time experience and I was able to complete the task. Of course, it was not easy after hours of trial and error and learning to troubleshoot. I was glad I was able to complete the task. This was my first time using a Raspberry Pi, and for the first time, I think I did pretty well. I always like learning new things and I can't wait to start another project on it. I actually thinking about doing a security system for my door. I can't wait to start that. Thank you. I want to say thank you to everyone that helped me through this experience. Mentors were a really, really big help. I also want to say thank you to this program. I learned so much from it and would do it all over again. This program has taught me to be inspired. It has guided me and pushed me to do my best every single day. I also enjoyed all of the many lessons that were thrown through the course. I learned a lot from them and it really made me want to do STEM even more than I already wanted to. So I really enjoyed it. I really am excited for my future. So thank you.
Our next presentation on the robotics team is rainbow measuring tape.
Hello, my name is Jeray Davidson. I will be a senior at Atoka High School in Atoka, Oklahoma, and I am a part of the NASA robotics team. So some background and goals for my project. I originally had 2 ideas before I landed on my final device. My main goal was to make something fun and creative, but also something helpful and useful. My first idea was for a tracker vest you would put on your dog that connects to your phone. So say if your dog runs away, all you would have to do is look at your phone to see where they are. The main reason I decided against this project was because I have a very little 3-pound Yorkie right here to the right, who is very little, so she wouldn't be able to actually wear the device since it would be so bulky and big for her. My second idea was to have a device that could sense if a person is 6 feet away from you. Since COVID, a lot more people have been extremely cautious about others and try to keep themselves distance. This device would have an LED that would light up either green if they're 6 feet away or farther, and red if they're closer than 6 feet. I decided against this because it seemed a little simple to accomplish and I really wanted to push myself. So this is my final project. The rainbow measuring tape. I'm sorry, you can't see the actual here. It says the rainbow measuring tape used an ultrasonic sensor and an RGB LED to determine how far away an object is. And here, an ultrasonic sensor, which is circled in blue over here on the left, that sends sound waves in whichever direction you point it. Once it bounces off of something, they'll send the sound waves back to the sensor, and depending upon how far away it is, how long it takes to receive the signals back is how far away the object is. The RGB LED, which is circled in pink, uses 3 colors, red, green, and blue, to make the LEDs light up in whichever color. And I have this device set up so that when the object you're pointing at is 1 foot away, it turns red. 2 feet away, it turns orange. 3 feet yellow. 4 feet green. 5 feet 6. 6 feet purple. Or 5 feet 6. Sorry. 5 feet blue. 6 feet purple. And 7 feet is pink. The rainbow case pictured to the right is something. It was supposed to be the housing for the device to determine whether to make it actually wearable. Unfortunately, I didn't have enough time to complete it, but it was very close. I had it to where it's just the computer would get very hot on my arm, which was, I'd prefer to have it. It's more of a safety issue than anything else at the moment. I would have included a picture of my code, but it's very hard to get it off of the actual computer that we use, and to actually show it all in one picture. But the code was definitely the hardest part of this whole process, because it's very hard with having only one LED to try to determine how to make it each different color, and especially trying to make it in between a range of a distance, like from 0 to 30 centimeters, which would be 1 foot. It's very hard. It took me a while. I think most of my struggles and stuff with this project were on the code. So I have a video here of my actual demonstrating my project. Sorry ahead of time for my dogs, because they are very loud. So they are very loud and tend to be annoying, especially during this video. Also, at the end, you'll see that it goes from purple to red, then back to purple, then to pink. See, toward the end of the actual spectrum of the light, the farther away it gets, it's harder for the sensor to actually get back the sound. So sometimes if something gets just too far away for it to hit, it'll make it go back straight to 0, which is why it turns red for a second. So it has to basically think for a second, oh, hold on, I actually have to still sense something, but I'll show you the video. See how it flashed from purple to red to pink? That's because it has a very hard time sensing something. So I would like to thank my mentors, from my NASA robotic mentors, Sherelle Webb and Gerald Holito, I think his name is, and to the SEED program for such an amazing opportunity and experience has been. So some highlights of this internship. I think that the best part of this experience was that it really opened my eyes on my future possibilities and made me really think about what I want to do with myself in the future. Not just a general what I want to do in college, but also what I want to do as a career, as an adult. It also made me realize that just because I'm a small town girl in Oklahoma doesn't mean that I can't do anything so amazing. Nobody expected me to even get into this internship to begin with. So it was much a surprise, and everyone in my entire town freaked out about it. And I'm just so grateful that this even happened to begin with. So some challenges were that it was online, because it was so hard for me to communicate with people online. I'm really such a visual person. I have to have someone visually with me for me to comprehend what they're saying. So it was very hard for me to get my instructions on my projects, and I still got it done. I still figured it out. I feel like it was probably a lot harder for me than it would have been for a lot of other people, but I still powered through it because this is really amazing, and I was really excited to be in such an important and exciting situation. I do understand though that COVID is the reason why, and I'm very happy that I got to do it at all, that they didn't just cancel it like they did for a lot of things because of COVID. But I hope that for everybody next year that they actually get to be in person and get to meet everyone on their team like in person and get to hang out and become actual like close friends. But thank you.
So our next robotics project is the diabetic alert necklace and mask.
Hello, my name is Ian Pena. I am from the Rio Grande Valley down here in South Texas. Today I will be presenting the diabetic alert necklace and mask that I have been working on during this internship. So starting off with my project background. My project background is based on experiences my mom has told me her type 1 diabetic friend goes through with a diabetes alert dog. She will have sudden changes throughout her day and is usually awakened or alerted by her dog, but as a result, she will wake up with scratches on her forearms. This got me thinking of not only her, but people who have a genuine fear of dogs, as well as those who have severe allergies. So I began to think, what could I do that could do the exact same job the diabetes alert dog does, but there's no dog involved. So for people who don't want to get hurt, like I said, sometimes they wake up with scratches if they have to wake you up, the dogs have to wake you up. People who are actually afraid of dogs and people who are allergic, so I got to thinking about that. So the first things I had to research was, the first few things I had to think about was, how do dogs even detect when you have a sudden change in your blood glucose level? So what I was interested in looking for was how to detect it, how to be able to detect what was being given off the body. It's called isoprene, and a chemical compound's called isoprene. And I also wanted to know what would be considered normal in isoprene levels. So here's what I found. I found that diabetes care dogs sense the smell of a chemical called isoprene that's produced by a chemical reaction when there's a sudden spike or drop in glucose levels. So the actual thing that the dogs are smelling is isoprene. They can smell this through the breath of the person. So when you're breathing, you give off a certain amount of isoprene in your breath. And when you undergo these sudden chemical changes with your glucose, the isoprene tends to go up. It tends to spike as well with the glucose, or the glucose drops, the isoprene tends to spike. And the dogs pick up on the isoprene and they let you know that something's wrong. Okay, for the next question, I found that isoprene can be detected in the air by gas detectors. And it has to be certain types of gas detectors, because some will only detect certain things in the air. I also found that isoprene levels is a consistent change relating to age. So if you're 12, you're going to have different isoprene levels as someone who's 50. So that I found that interesting, and I found that could be a kind of a hurdle to go over. And I also found that the average person average person, as in like 30, around the age of 30, like 20s, 30s, their levels should not exceed 50 parts per billion and should not go under 27 parts per billion. And by that, they mean parts per billion, like 50 parts per billion in the air. Like that's how they count it. I had no, not a lot of time to understand that part. So my build, it's all, how do I say this? It's all undergoing work. I feel very sorry that I could not get any worthy pictures. And I mean, I was running a little low on time. But this is how I imagined it to work. So it is a necklace and or mask. So in the necklace, there would be a sensor, of course, a gas sensor that would detect the levels of the isoprene around the person's being. So I chose a necklace or mask because they're the things that are closest to your face, closest to your mouth. And I thought that would be a good idea. So for the alert part, I envisioned that the necklace and mask would emit a beeping sound to let you know, as well as the necklace would vibrate because you can wear it while you're asleep. Sometimes the noise won't wake you up, or the light. The LED light, there would also be an LED light that would flash. So I combined the beeping sounds, the vibrations, and the LED lights to make sure that the person that's using it would be alerted. And then there would be a reset, of course. And then after the user has been notified or alerted, that they will press on a button, allowing for the alarm to reset and stop detecting isoprene levels for 30 minutes. Because in those 30 minutes, you would be able to inject yourself with glucose, the glucose shots, as well as be able to, I mean, you are already alerted, so you'll be able to monitor it yourself. And it would be annoying. It would be annoying if the thing kept going off. So that's why I wanted it to have a time for it to reset. So some challenges with the program, I felt like there was the communication was great. We did our best, but the whole Zoom thing is a little difficult, and we're all still trying to come together about that and figure that out. So it was a little bit on the difficult side. The physical computation and understanding was a little difficult for the exact same reason. I had trouble with my breadboard a couple of times. So it was a little hard to get that to the mentors and allow them to help. But I was able to surpass that. Career influence. This internship has given me the opportunity to not only partake in hands-on activities in the field, but I was also given the opportunity to meet many different engineers and scientists who had all interesting jobs, and they had all sorts of insight for us. So this internship has really strengthened my desire to become an engineer. And I want to say thank you to Ms. Webb And to all the other mentors, as well as that's it. Thank you.
So our next robotics team is Uncle Frank.
Hello to everyone here. Whether through Zoom or YouTube, we are glad that you are able to make it. We are a small but powerful group of two. I'm Xavier Scott from Houston, Texas, and I'll be an upcoming senior at Cypress Falls High School. My partner in crime, or in this case, stopping crime, is Cameron Lightis from La Vista, Nebraska, and she'll also be an upcoming senior at Pavilion, La Vista High School. We are a part of the most wonderful NASA robotics team, which has helped mold the project that we have today. I would like to give a big thank you to Cameron for allowing me to name the project after a family member of mine, Uncle Frank. He always gave the biggest hugs that shielded and protected me, and this project reminds me of him. But before we get into the project, we have to talk about the details of the project. One important part of this program is coding, which is a very specific and sensitive process. Coding is what allows us to be here today. It's in all the technology and apps that run, so it's very important to how the world continues to advance. It lays out the structure of whatever you're doing technology-wise. You could have 500 lines of code, but it won't run because you forgot to finish the parentheses in line 137. Madness, right? We use Python coding, which is like a programming language, which takes a little minute to learn, just like any other language, but it's totally worth it. We start out by learning how to print something simply like hello world in code, and then we eventually work our way up to attempting to type a full page on our own. I will break down the code that we use in our project later on, but it's just not coding that helped shape our project. It was also the Raspberry Pi and GPIO board. The Raspberry Pi is basically its own computing system. So when I turn on my Raspberry Pi, it looks a little something like this.
So it's basically like your regular old Mac or HP Windows. Even has the time. Unfortunately, that is wrong. It's actually 428. But you see, it has a lot of similarities to a regular computing system. So it's a lot that it can do.
The GPIO board is what brings power from the Raspberry Pi to the breadboard, which gives us much more space to put what we need. We need to make sure that we plug everything in right into the breadboard or it won't work and have us stressing out for 4 to 5 hours, texting Mr. Gerald in panic. But I'm totally not speaking from experience. But this can happen from a wire to a resistor to even something as a number keypad. We have to pay close attention to what goes where because believe me when I say that if it's on the diagram, it's of your utmost importance no matter what. Cameron let us know that her goal and reasoning for this project was
because I feel very insecure when I'm home alone, and I felt that way since I was in elementary school, and it was a really bad anxiety thing. And sometimes I would just sit by my window and literally not move until someone else got home for hours at a time. I wouldn't even get up to eat or do anything. And I would always peek out the window and make sure no one was coming up to the house or anything like that. So it really, really scared me. So building a security system is actually something that I would feel safer with myself. So my goal of building a security system was something to make people feel more secure when they're home alone or if they're leaving the house and they need to have a camera to watch it. So I just think that overall it's a very beneficial tool.
You could say our reasonings were along the same lines. I'm a flat out scaredy cat. I would turn on every light and shut every door and have kids bop in the background just so it wasn't too quiet. But it couldn't be too loud just in case the noise was made. So for me, what I hope I can do for others is bring a certain level of security to where you have no problem having fun all by yourself. For our project, we use 3 different codes and builds to combine into the Uncle Frank system. We start off with an easy LED pin, which consists of 2 wires and a 220K ohm resistor connected to the longer side of the LED. We then go on to the ultrasonic ranging build, which consists of more wires and 3 1K ohm resistors. Lastly is the doorbell build, which consists of a lot of wires and resistors, a button for the LED and buzzer, and a transistor, which regulates the voltage and current flow. This build could be seen as the most complicated because it covers a lot of the breadboard and has a lot to it. So when tweaking the builds together, we got a little something like this, and this is a little bit more in detail. Okay, here's my device. I'm going to run the code to show you that it works. Okay,
Okay. Now we're going to break it down. So this is my Raspberry Pi. This is like the power cell. This is what connects to my code and my breadboard. This is the GPI board, which connects the breadboard to the Raspberry Pi. This is what tells the Raspberry Pi which pins need power. So for example, I use GPIO 17 and GPIO 18. I know that's a little hard to see. So I'm gonna tell my code that I need power directly in those pins so that it can work. With my lights, you're always gonna have a 220 ohm resistor or it won't work. With my buzzer, use a 1K ohm resistor, and you always use a transistor, which regulates the current flow and the voltage flow. With my button, which regulates the buzzer and the light, you have 10K ohm resistors on both sides, and then you have wires connecting all throughout to ground in the pins that I need power. Okay, so that's the setup again. Now let's go to the code. As I said earlier, Python has many libraries, so you just go and pull whatever library you need, which in this case is rpi.gpio, and we want to shorten it to GPIO. Right here is GPIO 17 and 18, what we were talking about earlier. So you're saying I need power directly in those pins. Setup is just saying what you have and what it should be doing. So all throughout, you might notice that lead pin and buzzer pin have the same thing all the time. And that's because you want it to turn on at the same time and off at the same time. Button pin is just telling you what the button should do when I press it, release it, and all its functions. When you go to loop, this is where the circuit actually starts to work. A while true loop means it goes on forever unless interrupted. So right here it's saying if I press the button, it should turn on, both the buzzer and LED. And if I release it, they should both turn off. And you know it's working because it's gonna print what's happening. So if I press it, it's gonna print buzzer and LED turned on. And if I release, it's gonna put buzzer and LED turned off. If none of that works, then it's going to use GPIO.cleanup to just destroy the whole code and send everything back. So when you press start, it's gonna put program is starting, and then it's gonna put the setup, so it's gonna let you know everything it has. Then it's gonna put the loop, so then the circuit actually starts to work. But if it doesn't work, it's gonna do destroy. And if it does work, then you can press Control C to stop it, or you can use the stop button up here. So your results will always print down here in the shell. So right now, I'm gonna press it, and you see it's gonna spam that until I press it. It turns to on, and then when I let go, it goes back to off. So I'm gonna show you stop, and this is what I mean when everything is important. So if I get rid of these parentheses and I try to run the same code in the loop, this is what's gonna happen. You're gonna get an error. So it's important that you make sure you have everything intact. And with that, there's always room for improvement. So Cameron and I are now working on taking the project even further. So instead of the ultrasonic range sensor just letting you know how close something is or someone is, it would automatically go off and if someone was within a certain distance. The button would be a switch. If you flicked up or down, it would automatically call the police. And if flicked the other way, then it would turn off. The button instead would be used to power the whole thing. So the button would be what you press before you leave, which will trigger it so it starts detecting the distance. Then if something was close enough, like 3 feet, then the light and the buzzer would go off and alert you, and you would choose what to do from there. This will help to ensure that we are taking even more precautions.
Both Xavier and I would like to thank Mrs. Sherelle Webb and Mr. Gerald for the continuous help and support with assuring us that we were capable of doing it.
Cameron states that
the biggest challenge of this internship was actually the physical computing, because you could mess up one wire and the thing wouldn't work, and then you'd have to trace back every wire and every piece to find the one that was messed up, and that could take a lot of time. But the best part of this internship was the speaker series on Tuesdays and Thursdays, because it gave me insight about what my career could be like as an astrophysicist. And it not only shows what they do right now, but it also shows the steps that they took to get to where they are.
my biggest challenge will have to be online. When you get stuck, it's really difficult for your mentor to help you when they're not physically there. Also, I had to learn that it's okay to be mad and wrong, but I had to shake it off and bounce back even stronger. My highs were gaining wisdom and knowledge from my speaker series and mentors.
As Cameron stated, she was able to gain insight of what it really takes to be an astrophysicist. And for me, I gained experience that I wouldn't receive anywhere and realized that I'm very capable of living my dream as a scientist. We would like to show our gratitude to the SEEDS program at NASA for giving us an unthinkable experience. Thank you.
Great job. I want to invite the robotics team members that are online to turn your cameras on and your mics. We have a couple of minutes for questions. So for the pie hole project, could your invention be applied to more than just TV advertisements in the future?
Yes, I think so. I would like to do that improvement. And yes, I would like to apply it to more than just entertainment.
And Hike Alert, what was the most valuable skill that you learned?
The most valuable skill I learned was that for the goal of the device should always be safety. So like, what way can you just make your device safer for people to use? So yeah.
And diabetic, I don't believe our team member from the Diabetic Alert Necklace is online. So the rainbow measuring tape, how big does an object have to be in order to be sensed?
I assume it'd have to be a pretty decent size, like at least, I don't know, maybe like a foot or so, because it's so hard for something to like sense how far away the object actually is, you know, with it being pretty big. So it couldn't be very small.
And the Uncle Frank project, great description of coding in Raspberry Pi. What was the most fun part of your project and what was the most challenging?
The most fun part for me was just playing around with it, building different things, seeing what works together. And then the most challenging part was the code, trying to figure it out, figuring what works, what helped, what wouldn't work. So all that together.
For me, the most fun part was definitely, again, playing around with it and just experimenting and doing all the like practices we had leading up to it. But then the most challenging part for me was definitely the time restraint. Because even though I was struggling with like the physical computing, if I had like a little bit more time, it would have been easier to actually get it solved than just the time that we had.
And Hike Alert, do you think this technology could be incorporated into other devices? Would it be best to have it as a standalone device?
I think that in the future it could be used in other places other than hiking specifically.
And rainbow measuring tape, in what situations do you think that this device would be used?
I could see it being a like learning device for kids, you know, like helping kids learn like understanding like distance and learning colors and stuff like that. I didn't really see it it was not more of a practical device. It was more fun, to be honest, like just like though, because it's called the rainbow measuring tape. I think it's more for like kids and stuff.
And then Uncle Frank's project, what was the biggest inspiration in your project, other than you both wanting more security?
I'll let you go, Cameron.
Oh, I was just gonna say, yeah, it was mainly just the security thing for me. Other than that, I just thought it was kind of cool, and it was a fun idea to make.
As I mentioned in the beginning of the video, it was a reminder of my late Uncle Frank. He passed 2 weeks, so like this was like for him. I did this for him, like his protection. It was just all over me. So yeah, that was my reasoning.
Well, y'all all did an amazing job, and thank you for joining us today. We appreciate all the innovative ideas that you had in your robotics program. So our next project is the Mars Exploration Team. I want to give a special thanks to our project mentors, Dr. Hum Mandel and Adam Noakes, for their expertise and dedication. NASA is committed to the human exploration of Mars. Many of the technologies are already in place, and the rocket boosters and some of the spacecraft required are currently being built. The small nuclear reactors required to provide the necessary power have been designed and tested by the Department of Energy. But prior to sending humans to Mars, there needs to be an infrastructure on the planet's surface that is necessary to sustain the first crews that will visit. Using basic engineering design principles, Interns designed a Mars village that will allow people to live and work productively and safely for up to 1,000 days on the Mars surface. That might be a typo. I think it was 100 days. Small scale prototypes were being developed through CAD. So please join me in welcoming the Mars Exploration Team.
Thank you for joining us for the Martian Exploration Team, and today we're excited to share with you our plan for the establishment of a sustainable Martian habitat, which will pioneer the way for revolutionizing exploration, as well as lay the foundation for humanity to one day be able to call the red planet home. Let's get started.
Hi, my name is Eric Fitchner, and I'm from Parker, Colorado.
Hi, my name is Kate Williams, and I'm from Shawnee, Wisconsin.
Hi, my name is Elizabeth Halton, and I'm from Ithaca, New York.
My name is Mila Jones, and I'm from Fort Worth, Texas.
Hi, my name is Samantha Estrada, and I'm from Murrieta, California.
Hey, my name is Jay Shrivastava, and I'm from Glastonbury, Connecticut.
Hey, my name is Rebecca Patino, and I'm from Houston, Texas.
Hi, my name is Jonas Moreno, and I'm from Mill Valley, California.
Our program mentors are Dr. Humboldt Mundell and Adam Noakes. Our product associates are Marshall Morey and William Matthews.
Our presentation will begin with the structures, crew systems, and systems integrations team, then the environmental control and life supports team, followed by the communications and power team. We will conclude with our closing remarks and acknowledgements.
And now for the big question, why Mars? So in a nutshell, we must look to the past to answer this question. Insight, ingenuity, curiosity, perseverance, all words that embody what it means to be human. So the answer is simple. We go to Mars because we are human. We go because we must push the limits of our humanity and build the future that lies ahead for mankind. So I ask you this question, for that endeavor, what better place is there than Mars?
Our group was challenged to create a functioning Martian base that is capable of supporting 14 people for at least 26 months. We have decided that this base will be located at Jezero Crater.
Hello, everyone. I'm Eric, and I'm part of the Structures, Crew Systems, and System Integration team of Kate. Our goal was to incorporate all subsystems to create a cohesive base.
These are some of the requirements our group was tasked to fulfill. Our base will primarily host 7 people, but is capable of accommodating 14 in case of emergency. They will all be kept physically and mentally healthy with the necessary services provided. Our total radiation exposure for the astronauts will be less than 50% of their career limit so that it will be possible for an astronaut to have 2 missions to Mars. Our base will have 3 habitat modules, Dragon, Griffin, and Pegasus. Each habitat is equipped with an airlock and tunneling systems to other habitats with multiple exits in case of emergency. As you can see, the Griffin module has a rover port for direct transfer from pressurized rovers to the habitat, as well as a rover maintenance facility attached to the Pegasus module.
One of the challenges we will face on Mars is exposure to radiation. Radiation can cause many issues to astronauts, including lower cognitive function, increased risk of fatal cancer, and immediate effects such as radiation sickness. In our landing site of Jezero Crater, astronauts will be exposed to 0.43 sieverts for the 26 months on the surface. To put that into perspective, on Earth, we're exposed to only 0.013 sieverts for the same duration. On our base, we have been able to reduce the dosage from 0.43 sieverts to 0.232 sieverts, and that's about 15% of the female 35-year-old career limit for an astronaut. Our modules are designed to protect against the constant shower of radiation from galactic cosmic rays. The first layer of aluminum and Kevlar both serve the purpose of shielding against radiation and protecting against micrometeorites. Our next layer is water. All of the water will be in a closed system within the walls of the modules and will help also shield from radiation. Finally, the innermost layer of aluminum will be used to pressurize the modules and will also serve as the last layer of protection from radiation.
The top floor of the Dragon module will include 7 rooms capable of supporting 14 people. Each one of these rooms will be equipped with a bed, a cot, and a personal workspace. The Griffin module's top floor will include a gym that will accommodate astronauts in microgravity on Mars. It will also have an emergency room, communication center, and storage. The Pegasus module's top floor will mainly be used for the 3D printer space, lab space, and extra storage that is needed. Griffin and Pegasus will also include a window and a bathroom on each top floor.
On the bottom floors of the modules, Dragon will have a kitchen, that includes our greenhouse, a multi-purpose room, a bathroom, and an area for storage and lab space. The Pegasus and Griffin modules will be dedicated to more storage and lab space. Each module also has a ladder in the middle, and that allows for easy movement between the floors. The rover maintenance facility will serve 2 purposes. The primary purpose is to perform repairs on rovers and any other machinery for the base. The secondary purpose will be to further protect from radiation. In addition to galactic cosmic rays, solar flares are another form of radiation that Mars is subject to. Solar flares are high-energy particle events, and when detected, our crew will relocate to the rover maintenance facility where they will be better protected with a thicker layer of water in the walls.
18,000 kilograms of food will be required for this mission. This includes an assortment of irradiated food, which allows for more nutrients and a longer shelf life, dehydrated food, which will have a longer shelf life and lower mass, but a limited variety of food options, and thermostabilized food, which has a shorter shelf life, but tastes the most similar to food on Earth. Packaging accounts for 15% of our total food mass. A majority of this food packaging will be able to be repurposed by the 3D printer on board. Additionally, all of the food will be stored in international standard payload racks. We have decided to use the Texas Microgreens automated planter and processor as our initial crop production. It will include a food processing system and a fully automated compost. Even though it will only produce 140 to 300 kcal per day, it is still very important to start a foundation of crop production on our base for future missions, crew morale, and research on how growing plants can differ from planet to planet. In order to be self-sustained on Mars, we would need a large amount of space, mass, and crew time. For the initial mission to Mars, it is unrealistic to say that we will have access to all of these necessary requirements to fulfill this. Thus, this means we have decided to only bring 1 TMAP.
Now, Elizabeth and Mila of the Environmental Control and Life Support System Group will talk about their contributions to this project.
Hi, I'm Elizabeth. Mila and I are in charge of the Environmental Control and Life Support Systems, or ECLIS. ECLIS is responsible for creating an environment the astronauts can live in. It provides clean air and water for all crew members and systems for the entirety of the mission. The exact figures of these requirements are on the slide in front of you. They're provided for by 5 ECLIS units across the habitat, 3 are turned on, and 2 are backup.
The air management system regulates the atmosphere quality and limits the concentration of contaminants through filtration. The revitalization system recovers 99% condensate, maintaining a composition of 79% nitrogen and 21% oxygen. The oxygen generation system, or OGS, is connected to the water reduction system, where water is electrolyzed to obtain hydrogen and oxygen. Air with CO2 is processed through reduction systems, which processes a byproduct of water. The thermal control system regulates the temperature at about 73 degrees Fahrenheit and maintains a 60% humidity, and it also regulates air circulation. To address the low temperature of negative 117 degrees Fahrenheit, ammonia-based heating pipes and multi-layer insulation will be used. The Water Recovery System, or WRS, provides safe water for the habitat. The WRS recovers 93% of the water it cycles through. The cycle, which takes about 54 hours to complete, begins with the urine collection system, where urine is pre-treated with chemicals then combined with fresh water. The urine processor assembly produces a distillate, where the water processor assembly, or WPA, separates any gas from wastewater. WPA sends the processed water to a storage tank. All storage tanks are located in the walls of the habitat. Some water will be transferred to the OGS to aid in CO2 reduction before it gets recycled again. The fire detection and prevention system works on reducing the risk for fire propagation by keeping the oxygen concentration below 30%. and by facilitating fast reactions in the event of a fire. The trace contaminant control system has the capability to remove carbon monoxide and acid gas. Sensors detect temperature rise, combustion gas, and pressure rise. There will be both CO2 and fine water mist extinguishers. The major constituent analyzer monitors air composition, and the rack power switch allows the crew to turn off the entire rack in the event of a fire. Waste management focuses on recycling and disposing of waste. Solid waste is separated where wet waste continues to the wet waste processing unit, which recovers water. The 3D printer recycles plastic and foam. The remaining solid waste is addressed by the Orbital Syngas Commodity Augmentation Reactor, or OSCAR. This reactor utilizes the idea of trash to gas by converting waste into hydrogen, CO2, methane, and water through heat. Any leftover waste, called slag, is combined with glass to create non-toxic building material. Urine is collected and sent to the water recycling assembly. Plant waste is composted by TMAP. This all supports a zero waste system. Elizabeth will now elaborate on the storage of the ECLIS systems.
These systems are stored in modified international standard payload racks. These are the racks used on the ISS and other spacecraft that have been modified to fit our exact dimensions. You can see a CAD of these on your right. The extravehicular activity suits, or EVA suits, are what are worn by the astronauts as soon as they leave the habitat to explore Mars. We are implementing the proposed MEMU suit design that is currently being designed for the Mars environment. They are an adaptation of the currently used EMU design for the ISS. We will have 10 suits on the spacecraft, 7 for the main crew, and 3 to provide redundancy. Repairs in the habitat will be covered by a 3D printer. This printer turns plastic and foam waste from packaging into filament that is then used to print out different repair parts. These parts are very useful, but the plastic has a limited amount of times that it can be run through the printer before it loses structural integrity. Here, you can see all of the ECLIS racks in the CAD model of the habitat. The ECLIS racks line most of the walls, and the EVA suit racks, which are designed specifically to fit the suits, are by the airlocks where they will be used. Now, onto communication.
Thank you. We're the communications team, and let's get started. Now, communication consists of 2 categories: transplanetary communication and local communication. Optimally, with a communications link between Earth and Mars supporting video, which requires a bandwidth of about 2 to 5 megabits per second, we can also support voice and telemetry data relatively easily. As for local communication, Jay?
Yep, so as for local communication, we're working on creating a versatile network which we can expand on in future missions, really focusing on laying down that foundation. And in order to do that, we want a network that is, as you can see on the screen, flexible and expandable, and it would also be very nice to be high speed. But I'll talk more about that in the future. For now, Sam with transplanetary communication.
And now for a deeper dive on Mars to Earth communication. Given that sending information directly from the Martian surface to Earth would be difficult, an alternate approach is needed. The figure that you see here makes use of 2 radio relay links, one from the surface of Mars to an aerostationary satellite orbiting Mars via UHF transmission, which is optimal for this shorter distance, and another link from the satellite to Earth's deep space network via a high-gain antenna, which focuses the radio transmission to optimize signal strength, accuracy, and range over long distances. Now, a satellite for a manned mission must have more expanded capabilities than what has been used in the past, namely the Mars Reconnaissance Orbiter. For this reason, the satellite we will use will have more antennas, thus making it capable of establishing relay links from multiple directions, will support a higher bandwidth through the use of Ka frequency, which is 4 times more efficient than what has been used in the past, and therefore will be capable of supporting video consistently. As for communication during blocked windows, such as when Mars is blocking transmission to Earth, a relay link between the primary aerostationary satellite and a secondary satellite in polar orbit will be established, thus ensuring continuous communications capabilities between Mars and Earth. Jay?
So now for communicating on Mars, or local communications. And just for a little bit of context, to explain more, the main local communications will consist of either communicating from different buildings in the HAB, such as the Greenhouse and Communication Center, or communicating to things like rovers. And the primary method that we chose to carry this out was small sats, as you can see on the screen. By definition, they're specialized miniature satellites. This means they're about 180 kilograms, and they're about the size of a kitchen refrigerator, which in terms of space is extremely small. And the reason they're so interesting is because they're so small. They're so low cost and easy to build that you can easily get a lot of them into Martian orbit, creating a fast network with little to no cost. They act as part of a larger infrastructure in order to give data, as they can act as assets that both give and receive the information. And they also use ultra high frequency, which is optimized for its distance. Again, I cannot stress enough, these things are revolutionary in terms of space communications, and you'll definitely be seeing them more in the future. As for our redundancy strategy, we chose to adopt a system called MarsNet, which takes use of the 2 satellites that Sam mentioned earlier. These also use ultra high frequency due to the local distances, and how they act is by using orbital relay nodes, which, as I can say again, is sending and receiving data to assets. These things, as you can see, are scalable, fault-tolerant, redundant, and extensive. The reason why they are all of these things is because they take advantage of impromptu window openings instead of the planned IP-style delivery which systems previously used, making it up to twice as fast and more reliable. Now I'm going to hand it on to the power team. Jonas and Rebecca, take it away.
If you lose power on Earth, you tough it out for a few days. If you lose power on Mars, you die. Dr. Mandel. Having enough power is essential to the functionality of the mission and the survival of the crew. So it was Jonas and I's job to investigate how much this mission would require and find out how we would allocate all of it. We concluded that we would need to produce about 46 kilowatts and decided that the best way to do this would be using 3 small nuclear reactors and 2 different types of solar arrays. Here's the power breakdown for the estimated power budget. Now we will introduce how we will go about obtaining it.
20 months before our crew ever touches down, an Earth return vehicle carrying an in-situ resource utilization unit, ISRU, and 3 kilopower reactors lands on Mars. Instead of bringing all of the rocket propellant needed for the trip back to Earth with us, the ISRU, which is essentially a small chemical processing plant, would take the readily accessible elements in the Martian atmosphere and convert into fuel for the return flight home. This method drastically decreases the overall mass and cost of the mission. The ISRU will require about 23 kilowatts of power, and all that power will be supplied by the 3 kilopower reactors, which can produce up to 30 kilowatts. Although the ISRU will require a large amount of power to produce the fuel, the propellant will be made and ready within that 20-month period before the manned mission leaves Earth. So only a small amount of power will be needed to keep it at the required temperature once the crew arrives. Most of the 30 kilowatts of power will then be redirected to the Mars base.
These kilopower reactors, individually referred to as CRUSTY, are nuclear fission generators that use uranium-235. Each CRUSTY weighs 1,500 kilograms, generates 10 kilowatts, and has a large radiator that folds up for transportation. The 3 CRUSTYs will run during virtually any condition on Mars and are tolerant of dust, unlike solar arrays. It is our most reliable energy source and therefore will be in charge of producing the 22 kilowatts needed to produce all of the life support subsystems.
20 months after CRUSTY first lands on Mars, the Compact Telescoping Surface Array, CTSA, along with the rest of the mission base, touches down on the red soil of Mars. The CTSA lands on Mars in its stowed form, fitting inside a 10-meter lander. Its design has many variables that allow for any desired stow and deploy geometries and has been designed to withstand the Martian environment. Once in its secure location, the 6 solar array rings around the lander autonomously deploy. Fully extended, their length measures 22.5 meters, with all 6 wings providing a total solar area of 1,000 meters squared. The CTSA produces up to 72 kilowatts of energy during clear summer days and 45 on clear winter days, and will be responsible for providing the remaining power required by the base. During the day, the excess energy produced by CTSA will charge the 3 lithium batteries located within the HAB modules, so that the nighttime power needs of the base can still be met.
All of the stationary equipment's power needs will be completely met by the CTSA in kilopower reactors, but mobile equipment such as rovers need to be self-sustaining and require a lightweight, transportable energy source. The Ultraflex solar array is ideal for this application, as it is very compact and lightweight and holds up for transportation. Its design can easily be adjusted to meet specific power requirements of different kinds of mobile equipment and can produce about 7 to 12 kilowatts. For power storage, we'll be using 3 lithium batteries that will be placed underneath the floor of the HAB. As previously mentioned, these batteries will be charged by the excess power generated by the CTSA. The batteries utilize Xeon Power's Lithium technology, which has an ultra-high energy density of 640 watt-hours per kilogram. Each battery weighs 271 kilograms with a volume of 1.5 meters cubed, and the collective energy storage of all 3 batteries is about 520 kilowatt-hours. That is enough power to support all the life support systems for 24 hours, as well as some other subsystems, assuming ECLSS can slightly cut down on their power draw during an emergency. So in the case of a power emergency where there is a total loss of electricity, when the batteries are fully charged, it will give the mission crew 24 hours to fix the issue before their lives are in imminent danger. If the power cannot be brought back online, that is also enough time to plan an emergency evacuation to the ERV.
With 3 kilopowers, the CTSA, and 2 ultraflex arrays, we will be able to produce a minimum of 89 kilowatts during the day with a maximum of 126 and a constant 30 kilowatts at night. These energy sources, along with the lithium batteries, will easily supplement the needed power of the base and allow for the mission to operate smoothly.
Overall, our total mass for this base will be 188,000 kilograms. Our total cost will be $8.6 billion, and it will require 8 launches to transport this mass to Mars. Using 2 launches per opportunity, which is roughly every 2 years, it will take 8 years to get this infrastructure on Mars with a budget of $1.1 billion per year. Now, I will hand it off to Kate to talk about how this internship impacted all of us.
Throughout our experience, we have all learned so much about mission design and our futures in STEM. Our mentors have been so helpful and supportive, and I speak for the team when I say that it was their guidance and enthusiasm that transformed an already great experience to a phenomenal one. So thank you.
That concludes our presentation, and thank you for your time. But before we finish, we'd like to thank both our mentors and the SEAS program and staff members for this amazing experience that we got a chance to participate in. Now we invite you to ask any questions that you might have.
So I invite the Mars exploration team to please turn on their cameras and to unmute their mics. The first question is, would you be willing to go to Mars yourself?
So I can take this question. Personally, what motivated me most to want to be on the Mars exploration team is because one day my dream is to go to Mars. And so my answer would be yes, 110%. My life dream is to go to Mars one day.
And the next question is for the structures team. What criteria do you have for where to set up your base?
Sure, I can answer that. So we decided to land in Jezero Crater. And I'll say the primary reason for us landing there is that there are signs that show that Jezero Crater was an ancient lake. And so this has its benefits for we can actually mine that regolith and obtain water and other resources that could be useful for missions to Mars. And this will also enable us to search for any ancient life that actually might be there.
Another question for the structure team. How will this internship help you in your future plans?
Personally, like I said before, my hope is to go to Mars one day. And so it really helped me see what a future in STEM and more specifically Mars exploration like design looks like and working with others. And so it kind of really motivated me for my future and what it's going to look like. So.
And to chime in on that, I actually want to be an aerospace engineer or a mechanical engineer. And so this really gave me that experience with not only CAD, but I also got to explore different problems that I might encounter when I'm working on future projects within the space field and potentially for other space organizations like NASA.
Great. So what are some of the challenges in building bases on Mars?
Go ahead and take that question. One of the really hard things is the temperature, especially when you're thinking about putting things there like water, you have to really consider that. And also it's so far away that you have to really consider what you're going to take and the mass of it. And if you want to actually be able to bring that. So that's something that's definitely hard to address.
So this question is about communication. What is the redundancy approach to the 180 kilogram small sat units?
I'll take this question. So I think I mentioned it briefly in the presentation, but essentially what we're going to be using for transplanetary communication is 2 satellites, one which is aerostationary around Jezero Crater and one which is in polar orbit. So we're simply going to repurpose both of those satellites in order to use impromptu window openings, and that way we can find a way to get limited communications on the Mars surface. But in an ideal situation, the whole system of small sats should not fail as a whole, worst comes to worst, maybe one or two of the small sets failed due to collisions or something such as that, but the whole system should never go down.
What will astronauts do to maintain their mental health?
I think Kate can best answer this question.
Yeah, so I did a lot of research on the Texas Microgreens automated planter and processor, and that really showed the importance of having green in their habitat. Just the presence of fresh produce has shown up so many times to improve astronauts' mental health, just adding a little bit of normalcy. And yeah, so I think that's a huge thing and why it was so important to us, even though it is kind of an inconvenience, but the mental health benefits outweigh all of that. So we decided to bring along a greenhouse.
And actually, to chime in again, we actually also have a multi-purpose room. And in this room, it's going to be used for work as well as other activities that they will do that's not relating to experiments. So they can be just playing games together in this room, and that will really help with their mental health.
So the next question is, how will the communication time lag between Earth and Mars affect the response to emergency situations while on Mars?
I can go ahead and take this question. So this is actually first an amazing question, really. And I guess I can answer part of it, I would say. So in the time lag aspect of it, you do have a problem of when you're closest to Earth, the communication, you can get a signal to Earth in approximately 4 minutes. But when you're farthest away from Earth, you will get a response back up to 40 minutes. It'll take up to 40 minutes. So that's definitely really difficult. So that time lag, that time difference means that when you're farther away from Earth, you're going to be mostly on your own. You're going to have very limited communications, which is why it's very important that for a Martian exploration team, we need to have multiple people with different skill sets that are able to approach and tackle different problems when you have those issues. So yes, there is some support when you're closer to Earth, but if there's an emergency situation when you're farther away from Earth, then you will have limited support.
And I just wanted to add a little bit of context because I realized there was a little bit of an.
Is it possible for you to turn up your mic?
1 second, I will do my best. Is this any better?
Yes, much
Okay,
better.
sorry about that. But I just wanted to chip in real quick because I realized there was a little bit of an assumption or prior knowledge in the question itself. So it is just because of the way speed works, not possible for instantaneous communication between Earth and Mars. The maximum, just because of how the wavelengths travel, is 40 minutes, and that's the closest we can get to live feed. So, I mean, I think Sam handled that question really well. The best way to prepare for it is just to have people who are qualified to deal with those situations at Mars.
The next question is, what software was used to create your models?
That's a good question. We use Autodesk Fusion 360 to create the models, and I use Blender to make this rendering right here, as you can see on the poster.
Great. For the power team, does the system produce nuclear waste? And if so, how do you deal with that?
I can answer this one. So the crusties are nuclear reactors. So yes, they do. They have nuclear emissions, but we just kind of let that be. They have to be at least 1 kilometer away from the hab. So it's far enough away not to affect us or the astronauts.
And then I want to say a special thanks to all of the aerospace engineering team. You have done an amazing job. I think you could plan our next mission to Mars. So thanks for joining us today, and thanks for all the great answers to the questions. So our next project is the Astrobiology group. We want to give a special thank you to their project mentor, Terry Henry, for her support and creativity. One of the current advancements in astrobiology is the discovery of many types of extremophiles. Extremophiles are the microorganisms that live and thrive in environments that would be fatal to us. In this project, the students brainstormed questions and researched these unique microorganisms, including those that thrive without oxygen. They live in high temperatures and under chemical stress factors. The interns learned about the similarities and differences between Earth and Mars environments, along with the different types of extremophiles that can be found on Earth. They explored these microorganisms to determine which extremophiles could potentially exist in specific environments because of their unique form of obtaining energy from those environments. There will be 5 astrobiology team presentations followed by Q&A at the end. So please post your questions to Slido by team number. Our first astrobiology project is extremophiles on Europa.
Hi, my name is Anish Arade, and I'm from Harrisonburg, Virginia.
Hi, my name is Anisha Krishnamurthy, and I'm from Miami, Florida.
Hi, my name is Rajasika Hudker, and I'm from Houston, Texas.
Hi, my name is Oliver Ortiz, and I'm from Dallas, Texas.
Hi, my name is Mira Ravi, and I'm from Austin, Texas. Our astrobiology project studied extremophiles on Europa.
Extremophiles are organisms that thrive in extreme conditions. Because of their resilience, it is plausible that some could tolerate extraterrestrial environments. Our research asks, which extremophiles could survive on Europa? Our study could help us better understand the possibility of extraterrestrial life by connecting our knowledge of extremophiles with astrobiology.
In our research, we first explored various celestial objects and selected one to study further. We then identified the conditions at that location, including temperature, humidity, and radiation. Finally, we researched and identified extremophiles that could survive in these conditions.
We chose to study Europa, a small moon of Jupiter, because it is one of the most promising places to find life in our solar system. It has a thin oxygen atmosphere, and its surface is covered with a water ice crust. The potential for extraterrestrial life is found beneath this crust, where scientists have found strong evidence of a vast salty ocean of liquid water, which is shown in the lower image. Past spacecraft observations have suggested that plumes of water are ejected through Europa's crust, which could be caused by geological activity. This could provide the energy needed for life to develop.
Europa's surface is very cold, reaching lower than -350 degrees Fahrenheit, and is exposed to amounts of radiation that would be instantly fatal to humans. However, Europa's liquid water ocean has a very warm temperature of 39 degrees Fahrenheit and very little radiation exposure. Europa's water pressure ranges from 130 to 260 megapascals, and its oceans are very salty and acidic, with a pH of 2.6.
By comparing microbes with these conditions, we determined which extremophiles could potentially survive on Europa. The first microbe is Deinococcus radiodurans. This bacteria can survive massive amounts of radiation because it has multiple copies of its genome and rapid DNA repairing abilities. This microbe can also withstand acidic environments and temperatures of 37 degrees Fahrenheit. This bacteria has even survived 3 years outside the ISS in the module shown in the lower image.
Another extremophile that could survive life on Europa is Coelia cicatrarea, a bacteria that thrives in cold temperatures. It grows between 30 and 36 degrees Fahrenheit, thrives in high salinities, and withstands between 60 and 140 megapascals of water pressure, which all match the conditions of Europa's ocean. While only 2 extremophiles fully matched our criteria, others came very close.
Natrialba magadi is an archaeon that thrives in hypersaline liquid environments. It has a special cellular structure that uses charged amino acids to prevent dehydration. It is considered an alkalophile because it can withstand pH levels as high as 9.5. In past experiments, it has survived some conditions similar to those on Europa. However, this microbe thrives in temperatures and pH levels much higher than those on Europa.
Sulfophosphate is an archaeon that utilizes magnesium and sulfur to synthesize simpler compounds. Both of these elements have been predicted to be plentiful on Europa. This microbe also survives in pH levels as low as 2. In experiments, it has survived conditions similar to Europa's. However, it thrives in temperatures that are much warmer than those on Europa.
Our research has multiple applications. Learning about which microbes could potentially survive on other planets helps us better sanitize spacecrafts, as shown in the right image. By doing so, we can ensure that life from Earth doesn't contaminate other celestial bodies. The microbes we researched could also be used to determine what types of life to look for future space missions. Finally, the genetic traits of those extremophiles could have applications in bioengineering.
We would like to thank our mentor, Ms. Henry, all of the guest speakers, Ms. Miller and Ms. Baggio, for making SEAS possible. Here are our references.
The highlights of our internship included researching new subjects like Europa and learning from scientists. One challenge we had to overcome was negotiating amongst ourselves. Here are our individual reflections on our internship experience. Thank you for listening.
Our next astrobiology project is Impact of Microgravity on the Efficiency of Antibiotics Produced from Fungi.
Hello, everyone, and welcome to our presentation on the impact of microgravity on the efficiency of antibiotics produced from fungi.
I'm Carolyn, and I'm from Boston, Mass.
I'm Suhani, and I'm from Austin, Texas.
I'm Noelle, and I'm from the Woodlands, Texas.
And I'm Leah, and I'm from Fort Worth, Texas.
Our experiment looks at the effectiveness of antibiotics derived from the fungi Penicillium chrysogenum, grown in microgravity on the International Space Station, and their effectiveness against potentially harmful bacteria. We all had an interest in biology, medicine, and space, and we wanted to create a project that would combine these interests. We learned through the SEAS speaker series that fungi have a faster growth rate in space, and through research we found that fungi could withstand radiation up to 200 times the dosage that would be fatal to a human. So we were interested in designing an experiment that could harness these unique capabilities of fungi to enhance antibiotic production to improve long-term space travel. Fungi are found in multiple habitats, and the CDC estimates there are 1.5 million species of fungi on Earth. Fungi are also involved in the production of more than 10 of the 20 most profitable products in medicine. For our experiment, we decided to use the fungi Penicillium chrysogenum, which produces the antibiotic penicillin. We decided to choose penicillium as the fungi for our experiment due to its low ability to cause invasive diseases, as well as its popularity and well-established reputation in the medical industry.
In our hypothesis, we believe that if Penicillium carcinogenum is produced on the ISS and then synthesized for antibiotics, then it can be concluded that the antibiotic strength in space is equally effective as it is on Earth, and this is because Penicillium carcinogenum can flourish and thrive in conditions on the ISS.
Now I'm going to walk you through the procedure for the experiment. 2 sets of samples of Penicillium carcinogenum will be sent to the ISS, while 2 sets of control samples remain on Earth. Both sets of samples will be kept at the same temperature and both in potato dextrose. 1 week after being sent to the ISS, 1 set of samples will be grown and synthesized into penicillin, which will then be sent back down to Earth. At the same time, 1 set of control samples will be grown and synthesized into penicillin. When both of the first round of penicillin samples are on Earth, their effectiveness will be tested with the disk diffusion assay, measuring the zone of inhibition. The image on the side is an example of this assay, and we would measure the diameter of the circle of fungal inhibition around the antibiotic disk. The second set of samples will be kept in dormancy for 3 months, so the experimental sample can fully adapt to the unique environment of microgravity. Then, the remaining set of samples and the corresponding control set will be synthesized using the same procedure. When both of these second round of penicillin samples are ready, their effectiveness will be tested. And this is an example of what the data table would look like when we had actual numbers and data to go in there.
Humanity is headed towards the stars. For future missions, especially long, deep space ones like Mars, it may be vital to have the ability to combat sickness. For these missions, it's generally not very energy efficient to bring months or years worth of medicine from Earth into space. If our hypothesis is proven correct, it would imply it's viable for those going on deep space missions to bring up a small amount of materials like penicillium used to make medicine and simply keep replenishing the supply on board when whenever needed. This would allow astronauts to be able to synthesize antibiotics they may need in space without much cumulative energy costs from bringing materials from Earth. This not only has applications for those in space, but for those on Earth as well. If materials grown for antibiotic production in space prove just as or more effective than those grown on Earth, this could be quite impactful for pharmaceutical companies. Scientists already recognize that microorganisms grow more rapidly in space. However, if materials synthesized from these space-grown organisms were equally or more effective than those on Earth, this would allow these companies to increase efficient remedy production, allowing more people access to vital medications when they need it.
William Arthur Ward once said, feeling gratitude and not expressing it is like wrapping a present and not giving it. So as we wrap up our presentation, we would like to give thanks to everyone who made it possible for us to be a part of this program and to learn so many wonderful insights in this amazing world of science. Thank you to Ms. Foxworth, Ms. Baggio, Ms. Miller, Ms. Henry, Dr. Redberg, guest speakers, SEAS program as a whole, and to all the viewers watching. We want to say thank you.
Good job. So our next presentation is tardigrades as model organisms for space exploration. Oops, sorry. Our next presentation is building an extremophile.
Hello and welcome to our virtual presentation on our research of building an extremophile to live on Mars.
Here's what we'll be covering today.
Hi, my name is Anoop Dyer.
Hi, my name is Brittany Segovia.
Hi, my name is Millie Lusick.
Hi, my name is Ella Sklar. Hi, my name is Henna Vilstecker. Extremophiles are defined as an organism that thrives in extreme environments. We wanted to design an organism using already existing traits among extremophiles that would thrive on Mars. We researched a specific area we believed would be suitable for life, selecting the site named Nili Fosse. Clay and rocks with amounts of silica are found here, caused by a past water presence, and telescopes have detected methane in this area. We also decided our organism we wanted to utilize these traits for would be a potato due to its ability to be genetically modified.
The primary goal was to be able to genetically modify a potato with the traits of existing extremophiles so that it would be able to survive on Mars and make it more habitable for human life. The following list are some steps we took to meet our goal.
In order to achieve our goals, we had to form a plan in which I will briefly explain the methods we chose to follow. We wanted our organism to be located on Mars, which would help us determine which traits to use. After forming this outline, we began researching to gather more information on our area and 5 chosen traits to figure out which organism would provide the best fit. Lastly, we compiled and shared our findings.
We wanted to make our potato photosynthetic to be able to make its own food. The extremophile I chose to look into was cyanobacteria. We plan to depend on the polypeptide protein complex known as PS1 and inject the enzyme ALC because they will both aid in creating energy for the prokaryotic cell in our potato.
My organism was a psychrophile, which are organisms that live in very cold temperatures. They are characterized by lipid cell membranes that are chemically resistant to the stiffening that traditionally occurs when organisms are exposed to the extreme cold. We selected an obligate psychrophile for our organism because they can live in more extreme temperatures. Since Nili Fosse's environment has a significant amount of methane, we chose the trait of methanotrophism to be able to assimilate the carbon within methane and generate ATP. We chose the extremophile Methylomicrobium burrietans, which is a type 1 methanotroph that uses the ribulose monophosphate pathway to create this advantageous backup metabolism source.
For the radio-resistant trait, I chose the extremophile D. radiodurans for its ability to repair DNA damage. The organism contains a REC-A protein, which helps speed up the recovery of radiation damage done to DNA strands.
For our last trait, we felt that it was important for our organism to survive with little available water. Xerophiles accumulate internal solutes to maintain a high enough osmotic pressure for survival and growth in really hot and dry areas. One specific xerophile is Aspergillus acraceus,
which contains the critical enzyme DG18. Being able to add all these proteins and enzymes into our potato will help it survive in areas that lack water, such as Nili Fosse.
Our results are the correlation between the environment of Mars and the traits given to an organism through genetic modification.
Our project has three main future applications. Firstly, for planetary habitation, our project would enable the sustainable long-term habitation of Mars, and this model could also be applied to other habitable planets. Secondly, for disaster relief, we could help terrestrial regions that are affected by natural disasters, like floods or droughts, to provide them with a consistent food source, as well as a way to revitalize agricultural economies. Finally, for in-flight cultivation, as the length of space missions increases, it's important to have a self-sustainable food source to help the astronauts. In conclusion, the genetic modification of the potato with specific extremophilic traits will optimize it for success and long-term growth on Mars. Overall, our experience with the season trip is extremely positive. Although we faced some difficulties with time management and creating our own schedule, we really learned a lot from the speaker series and were able to apply it effectively to our project.
A special thanks to each member of our team, Ms. Henry, Ms. Miller, Ms. Baggio, TSGC, and NASA for giving us this opportunity.
Here are our individual insights, and here are our sources. Thank you.
Good job. And the next astrobiology project is tardigrades as model organisms for space exploration.
Hello, everyone. My name is Tia Shende, and my teammates are Jaya Sharma and Kaden O'Keely-White. In this presentation, we will examine a remarkable extremophile and see how we can draw inspiration from its characteristics to expand the field of space science.
For background on tardigrades, they're a phylum of microanimals that inhabit a diverse selection of environments on Earth. And they also have been known to be resilient enough to survive a myriad of conditions such as extreme heat, extreme cold, pressure, acidity, and even the vacuum of space. Now, the main focus of this presentation is to see how do tardigrades protect themselves and, most importantly, how humanity can utilize this ability.
One way that tardigrades are able to live with such resilience is through a process called anhydrobiosis, or simply desiccation. This is essentially the rapid dehydration of their body as seen in the photo below, and the suspension of nearly all metabolic function. And in this state, they can survive almost up to 20 years. They do this using proteins that are specific only to tardigrades called tardigrade disordered proteins, or TDPs, which exhibit a non-tertiary structure. One specific subsect of TDPs are the mitochondrial abundant heat-soluble proteins, or MAHS proteins. These essentially protect the mitochondria during desiccation by maintaining space between lipid heads and rehydrated crystalline states, as seen in the photo below. An application for this desiccation tolerance for human space exploration involves preserving biological materials such as food and medication. This results in increased quality, and it can also be stored for longer periods of time. Also, we could in the future be able to preserve cells and tissues and also take desiccated tardigrades to space for research of what life is like in space.
Tardigrades, in their genetic defenses, have shown remarkable resilience to radiation, especially, particularly gamma ray and X-ray, and that variety. Up to 5,000 grays, the SI unit of radiation of gamma rays, and the ability to protect their DNA from X-rays. Now, while most tardigrades show this resistance, it is particularly two species, Paramacrobiotis VLR strain and Rhamazodius varionatus, which both show a remarkable tolerance for higher than the average tardigrade. Paramacrobiotis has a fluorescent coating, which allows it to survive UV and higher at a much higher tolerance, coating its body. And genetic sequencing has been done using Rhamazodius DNA on human genomes in order to test the resilience of tardigrade DNA. Now, the applications of this DNA work shows that genetic modification is possible, and we could possibly utilize this to make future humans more capable of surviving extreme environments.
The The protein unique to tardigrades that contributes to their extreme tolerance to radiation is damage suppressor, or DSUP. An experiment was conducted by engineering human cells with DSUP from a highly radiotolerant tardigrade species. After exposure to radiation, the engineered cells had less DNA strand breaks and maintained their proliferative ability, while the unaltered cells were damaged and non-viable. This experiment determined that as opposed to facilitating the DNA repair process, DSUP prevents DNA damage in the first place. If such a mechanism was replicated, not only in human cell lines, but in the human body itself, astronauts can be protected from the heavy amounts of space radiation on a subcellular level.
As a part of the NASA SEAS program this year, we found that some of the best features included our virtual flexibility on Zoom. Also, we all really enjoyed the speaker series, which showed us a range of research and jobs at NASA available to us in the future. Some challenges was that it was definitely more difficult to collaborate virtually, and it was also harder to find sources on our specific topic of extremophiles in space. And looking back at our experience as a whole, for me reflectively, I loved how the SEAS program showed me that you can really mix biology with space and the applications for that in the future and job opportunities.
As for me, the SEAS program has solidified my interest in space science, and I'm eager for more research experiences and opportunities.
And for me, this program has reignited my love of the cosmos and reminded me why I want to become an astrophysicist in the first place, just seeing those closer steps toward the stars.
As we conclude our presentation, we'd like to thank the NASA SEAS program, the coordinators, our peers, and our mentor, Ms. Terry Henry, for the great experience. If you have any questions, feel free to contact us through the email addresses provided. Thank you.
Very interesting. Thank you. And our next astrobiology project is analyzing the possibility of photosynthetic bacteria on Proxima b.
Hi, I'm Eileen Liu.
My name is Devin Bibikar.
I'm Lynn Morris.
Nicholas Folks.
I'm Tanvi Deshmukh.
And I am Neil Panth, and our project is about analyzing the possibility of photosynthetic bacteria on Proxima b. Our goal is to analyze the known environmental conditions on Proxima Centauri b and determine, using examples of photosynthetic bacteria on Earth, whether those types of life may be able to survive on Proxima b, and if so, what biosignatures could be present. Proxima Centauri b is an Earth-sized terrestrial planet that orbits Proxima Centauri, the star that is closest to our sun at about 4.2 light years away. Proxima b star is an M-type star, also known as a red dwarf, and is smaller and cooler than our sun. It's also located in the habitable zone of its star, where liquid water could theoretically exist.
To provide some background, a biosignature is a substance, characteristic, or phenomenon whose presence is an indication of past or present life. A biosignature is often classified as such due to it being the result of common biological processes. For example, photosynthetic cyanobacteria produce a biochemical structure called a stromatolite, which would be strong evidence for their presence in an environment. The job of many astrobiologists is to search for biosignatures in order to assess an extrasolar body's potential to house life.
After determining the elements necessary for the development of life, we began our research by studying the environmental conditions of Proxima b. By finding organisms that could both withstand and prosper in these conditions, we narrowed our search further. Within a small handful of organisms, we decided to focus on the bacteria Rhodospirillum rubrum, which seemed the most promising.
Proxima b is subject to extreme UV and X-ray radiation from its star Proxima Centauri. Because of this, the atmosphere, which is speculated to consist of the lighter hydrogen and helium, could be negligible or non-existent. If a thin atmosphere exists, there could be sufficient pressure to allow for the existence of liquid water on the surface, since the exoplanet is in its star's habitable zone. If surface water does or did at some point in time exist on the planet, then any existing atmosphere may also consist of oxygen or carbon dioxide. Oceans would be able to protect living organisms from the heavy radiation that Proxima b faces. However, there is also extremely strong wind as well as large pressure variations that would affect life. The exoplanet also most likely has a spin-orbit resonance with its star, but it's not known what the ratio is. If it's 1-to-1, one rotation to one orbit, then one phase would be very hot and the other would be extremely cold. If the ratio is 3-to-2, then the temperature would be more moderate.
We found that the bacteria Rhodospirillum rubrum could be used as a proxy to show that photosynthetic life could exist on Proxima b. Firstly, our rubrum is a facultative anaerobe, meaning that it can survive both with and without oxygen. Secondly, it has basic radiation protection. The bacteria has been used in multiple radiation studies and could potentially survive under harsh UV, X-ray, and gamma radiation seen on Proxima b. Since Proxima b receives EM radiation from the visible light and near-infrared spectra, the bacteria would be able to conduct photosynthesis. With the pigment bacterial chlorophyll A, the bacteria can conduct anoxygenic photosynthesis using near-infrared spectra. With the accessory pigment chlorophyll B, the bacteria can also access light from the visible light spectrum. This allows Rhodospirillum to use various wavelengths of light and adapt to its light environment, increasing its chances of survival on Proxima b.
As for the biosignatures from this photosynthetic life, it's unlikely that we'll look for specific colors of photosynthetic organisms, since many photosynthetic organisms can actually adapt and change the ratio of pigments that they use to fit those specific light environments. Instead, our rubrum especially can literally change color depending on its environment. Instead, the surface biosignature that we're talking about is the near-infrared edge. So on Earth, there exists a vegetation red edge, a very prominent biosignature of our planet that can be identified by using spectroscopy. It occurs because chlorophyll A, the photosynthetic pigment that is conserved across almost all photosynthetic organisms, sees a large increase in light reflectance at around 700 nanometers, just past the wavelength of visible red light, as shown in this picture. This is thought to be a mechanism to protect against overheating, and it's likely that photosynthetic bacteria on Proxima b would also have a similarly sharp spectroscopic feature. However, since these organisms would likely make use of near-infrared light, it's likely that this edge would occur at longer wavelengths than Earth's red edge.
As for the highlights of our internship, we enjoyed working in teams, connecting biology to astronomy, and understanding advanced texts. We had challenges coordinating virtually and understanding spectral data. Here are our personal reflections. Works cited, image citations, and we'd like to give a special thanks to Dr. Giada Arni for answering our research questions.
Good job for the astrobiology team. I'm going to invite all of you to please turn your cameras on and unmute your mics. We have several questions for you. The first question is for team number 1. How did you find the extremophile candidates?
So I'll take this one. So
Can you turn up your mic just a little?
Yes. Give me 1 second. Is this a little better?
Yes.
Okay. So when we first started our research, we wanted to pick a celestial body in which the extremophiles would survive on, and we chose Europa, which is a small moon of Jupiter, because we know that from previous research, scientists have proven that Europa's oceans have the most promising environments for extremophiles to survive on, because their oceans are very salty. So when we were researching the extremophiles, we went through their characteristics of it had to have a high pH level and they have to be able to survive in hypersaline environments. And that's how we narrowed them down to those top 4 that we picked.
And so the next question is also for team number 1. Do any of the extremophiles on Europa have similar characteristics to those that are found on Earth?
So I can take this one. Actually, those extremophiles that we talked about in our presentation weren't actually found on Europa. What our project was finding extremophiles on Earth that could survive on Europa.
Okay.
So they're from Earth originally, they're not on Europa.
Great. Have astronauts this is for team number 2, have astronauts tested penicillin on the ISS?
Okay, I can take this one. So they have indeed tested Penicillium chrysogenum in simulated microgravity. And on the ISS, they have indeed done research about microbial antibiotic production around the International Space Station. They have done stuff in relation to producing antibiotics, but they haven't done stuff in relation to seeing which is more effective, which is what we're going to be testing.
So this is kind of a follow-on to that question. Would there be known differences on how antibiotics act in space?
I can take this one. So it is known that antibiotics on the ISS are going to lose effectiveness over time, which is one of the inspirations for this project. If we can grow up the antibiotics right when they're needed, they're not going to have time to lose effectiveness. Like say you're 2 years into a 3-year mission, you don't want to take antibiotics that are 2 years old and aren't as effective as they need to be, but you also can't get a resupply from Earth. So with our project, you could grow up your own.
And this is also a question for team number 2. What alternatives to penicillin would you propose for those who are allergic to that antibiotic?
I can take this one too. With this experiment, assuming it's successful, we could use any type of fungal derived antibiotic. So our goal is to send small amounts of a ton of different types of fungi to have a pharmacy of sorts that you can take with you and obtain any antibiotic you need for a specific situation.
To chime on to this, sorry.
Yes, go ahead.
So, and a particular example of this is Aspergillus is another known specific fungi that is used for producing antibiotics that could also potentially be good for those who aren't doing well with penicillin.
And the next question is for team number 5. Would you seek bacteria on Proxima b or propose to introduce them to the planet? What perils or positive advances do you anticipate? Team number 5.
I can take this one. I think generally when we look at how NASA views extraterrestrial planets, we don't want to disrupt the atmosphere and the environment that's already been built up on the planet. So on that same note, adding a bacteria that from Earth onto that planet might not exactly be a feasible idea because we don't know how it might affect the life that actually lives there right now. And on a similar note, I think it is possible to find bacteria of different types there.
So the next question is for team number 3. How long do you think it would take to develop your potato now that you've identified candidate extremophiles?
I can take this one. So I think in terms of development, the probably most difficult part would just be trying to obtain these different extremophiles and make sure that we have, enough of them to develop a successful culture. The reason that we chose a potato, well, one of the many reasons, was because it has been genetically engineered a lot in the past already for like agricultural applications. So in terms of, I think obtaining it would be like obtaining the extremophiles would be the hard part and extracting those, DNA sequences or proteins. But once we have that available, I think putting it into the potato and the actual modification process would be quite easy. So in terms of how long, I can't really say definitively, but I would probably say, between 6 to 10 months would probably be an appropriate estimate.
What characteristics, this is for team number 4, what characteristics do tardigrades have for protection against radiation?
I can take this one. So among other things, they have like quite a few defenses that we've not only covered in the presentation, but also the fact that there's ongoing research into quite how resilient their DNA can be. So for example, not only can they survive radiation just by their normal hibernative state, which is called a TUN, is when they kind of demetabolize their systems and go into a dormant state. They also are able to possess certain species, but a lot of them possess damage suppressor proteins, which actively protect their DNA from any interaction with radiation. And it has been shown that it does protect it from radiation. In addition, there's ongoing research into species that have shown a certain fluorescent coating on their bodies, which has been linked to an increased tolerance of radiation of ultraviolet and higher.
And the next question is for any of the teams. What was the most fascinating thing well, actually, no, this is for the same team. What was the most fascinating thing you learned about the tardigrades proteins?
I can take this one again. So damage suppressors was honestly the most fascinating thing to me, because just the fact that, because our DNA, our human DNA and a lot of animals, they have reparation processes, but not necessarily processes to help negate damage as it is received. So finding out that tardigrades and researching the fact that tardigrades do possess that inherently unique ability, especially among other animals, was very fascinating to me.
I can jump in on that one too. Through my research, I found it was the most fascinating, the idea that the tardigrades, this TDP, this tardigrade disordered protein, is specifically just found in tardigrades as far as we know, and that this protein has the ability to protect the mitochondria in a state where the entire body of the tardigrade nearly dissolves and suspends metabolic function. So for me, that was what I thought was the most interesting and applicable to bacteria cultures in space, as well as biological materials.
And team number 3, how would you find extremophiles?
I can jump in on this one, but I'll just elaborate so that my team members also have a chance to speak. Essentially, the way we broke down our research is that we had 5 traits, and each of us, researched into these traits and subsequently found extremophiles that live on Earth currently and, kind of matched them up. So personally, for the trait that I said, which is methanotropism, there are a lot of manotropes that already exist. They often tend to be found in like cave environments or swamp environments. So in terms of obtaining them, there has already been work done where, I think it was Stanford University did research in the lab as to how they can recreate the optimal environments that methylomicrobium can live, and how they can recreate that in a lab for long-term research. So I think there's similar cases in that for the majority of our extremophiles, they have been researched in terms of how to find them, where to find them, and how to keep them for long periods of time in lab environments. So if anyone wants to elaborate, feel free.
So our last question is for team number 5. What biosignatures suggest the presence of life?
Probably the biggest one that is generally looked for is the presence of oxygen, because that would demonstrate that, it's not definitive, but that would likely, or that would be a sign that photosynthetic organisms exist on a planet. But obviously, like most biosignatures, there's a strong chance that it can be caused by abiotic factors as well, so not by life. So, but that's the one that they mostly look for. And then also the presence of liquid water is another thing that scientists would look for when trying to find habitable planets. But yeah, just the presence of oxygen, like a good amount of oxygen in the atmosphere, is the most common biosignature.
Well, you have all done a wonderful job. It was a very interesting project, and I want to thank you for your presentations today. So we want to give a very special thank you to all the student interns that presented today. Your research is amazing, and we all learned so much from you. While Selena Miller and I manage and organize the SEAS program, we could not do it without these amazing mentors and project associates. So we want to thank each of you for your time, your talent, and your commitment. Thank you for joining us for day 2 of the NASA STEM Enhancement in Earth and Space Science High School Intern Science Symposium. We appreciate the student interns sharing their research and reflections. Each of you are applauded for your work ethic, your commitment, and your presentation skills. We invite everyone to join us tomorrow at 12:30 Central Time as we highlight research conducted by the Globe Observer Earth System Explorers, NASA